to deliver a talk. Thank you. You want me to adjust this mic? Okay.
So can you speak?
My pen drive, yeah, there's another. And pocket, yeah. Okay. No, inside pocket. Now audible.
Now audible. Huh?
Audible.
Yeah, just have to connect this. Yeah. Audible.
You don't have to copy. You take it.
I got it. I got it. I got it. Got it. Got it.
Okay. Okay, let me try to save time as much as possible. This icon, not arrow.
It's fine. No, arrow won't.
Arrow.
Arrow will not be there, sir. I think this only will.
Okay. Okay, the title of my talk is generalization of core nilpotent decomposition of an element in the associative realm. So, in a matrix context, most of you know what the core nilpotent decomposition is. Okay, given a matrix A, you can split that matrix into two parts. One as a core part. Core part means a core matrix is nothing but a matrix with the invariant space. Okay, subspace. The column space is invariant. Or in other words, rank of that matrix is rank of square of that matrix. Such kind of matrix is called core matrix. And the other part is nilpotent, satisfying some condition. Nilpotent matrix means you raise the power of that matrix several times. At the end, you will have zero matrix. Okay. So I will come to that point again. So this work is part of my collaborative work with my students, Savita Parkade and Uma Shankar Kaltaya. So contents of my talk as follows. So let me skip abstract. You will come to know what I'm going to talk about. Okay, these are some important notation which I may come across later. So A similar to B over CS means these two are the elements from ring whose this is right ideal of A is equal to right ideal of B. Similarly, RS. This is from this terminology is borrowed from matrix theory. The column CS for column space and RS for row space. So this column space is replaced by a right ideal and row space is replaced by left ideal. Okay, the SP is for both row space and column space are equal. I use this direct sum again borrowed from matrix theory. So A direct sum B means so A plus B with this property intersection of right ideals generated by these elements and left ideals generated by these elements are 0. So let me introduce Drazen inverse to begin with. There may be many people not knowing about Drazen inverse. A matrix G is called Drazen inverse of A if GAG is equal to G. I write 2 with some intention. It is borrowed from Penrose's condition. And 5 is AG is equal to J. This A and G commutes. And A to the power K is equal to A to the power K plus 1 G for some positive integer. Okay. Okay, for some integer K. The Drazen inverse of A is denoted by A to the power D. The D is for Drazen inverse, and smallest integer K satisfying 1K is called a Drazen inverse, Drazen index of A. Okay. A matrix decomposition. Fine. CA into NA is equal to NA into CA is equal to 0. The sum A is equal to CA plus NA is called core nilpotent decomposition, and such a decomposition is uniquely exists. In the context of real or complex matrix, it should be a square and an integer k. The following statements are equivalent. The Drazen index denoted by I and DIT. The index of A, the Drazen index of A is k, and some scale or something. No, it's all right. I'll just stay near by that. Even pen is enough. I don't. Oh, no, this is required for.
Yeah. Just mouse.
Oh, even this one works. When it is everything.
Mouse you
I'll put it off.
Yeah.
And a to the power k is equal to a to the power k plus 1 y for some matrix y, and a to the power k is equal to z a to the power k plus 1 for some matrix z. So what does this mean? This means the column space of a to the power k is equal to column space of a to the power k plus 1. Okay, this inclusion is always be trivial. So in this particular case, that becomes equal. Here, this says that row space of a to the power k is same as that of row space of a to the power k plus 1. The equivalence of that condition 2 and condition 3 is trivial for the matrix case, but in general, it is not true. If I take the context to the associative ring, that won't remain true. In fact, the statement could be generalized to the case of associative ring with the identity only when the ring is with the bounded index. That means you take nilpotent elements of that particular ring and index of those nilpotent, all the nilpotents is bounded by some number. Okay, so if you keep the set of indices as integers, that set is bounded from. So we have the following questions. What could be the alternative for the Drazen index in the absence of Drazen inverse? Because the Drazen index is defined along with the definition of Drazen inverse. So if Drazen index is not there, then what is the alternative candidate for that particular notion? The second question is, do the Drazen inverse and core nilpotent decomposition always coexist? If one is there, whether other one will be there. Matrix context, as the previous slide shows the same thing. But in general, when I take this particular notion over the associative ring, whether it remains same, that is the other question. Then what are the possible generalization of core nilpotent decomposition and the Drazen inverse and their relations? So we like to have some alternative notion for core nilpotent decomposition. So what is it? So those are to be explored. So I have taken up that particular those set of problems in my earlier work with the Savita and Uma Shankar. Okay. So here are some definitions. Let us go through it quickly. So generalized inverse, that is an element A is regular in the ring A if there exists G belongs to the same ring A such that AGA is equal to A. In such a case, G is called generalized inverse or simply G inverse of A. An arbitrary generalized inverse of A is denoted by A minus, removing the minus 1. So we use that particular notation to denote an arbitrary generalized inverse. Outer inverse of an element is defined in this manner. An element G is an outer inverse of A if GAG is equal to G, and it is denoted by a to the power equal. 2 minus signs are used. Group inverse is a generalized inverse as well as the outer inverse, and additional property is AG is equal to GA. Those two commutes. Okay, whenever it exists, we will denote it by a to the power sharp. Okay. So Drazen index in the context of associative ring is defined this way. the Drazen inverse of A is the element G satisfying this is the outer inverse condition. The other one is commuting condition, and G into a to the power k plus 1 is equal to a to the power k. Here writing a to the power k plus 1 G is same as that of G into a to the power k plus 1 because of this particular condition. A G is equal to G A. Okay? That happens for positive integer k. The Drazen inverse, whenever it exists, denoted by a to the power d, as in the case of matrix. The least positive integer k satisfying the above condition is called the index of A or the Drazen index of A. So here, let me introduce another notation, pi regular element. An element A is said to be right pi regular if one of that condition earlier we have seen that A is equal to a to the power k plus 1 x. Okay. Similarly, left pi regular is defined when this particular condition holds for some integer k. Okay. Then in such a case, x is called right or left inverse depending on the context. Okay. The least positive integer k satisfying the condition is called right index. Earlier I called it simply index or Drazen index. Here we will denote it by this particular note, like right index. Similarly, left index is defined. So an element is said to be strongly pi regular if it is both left and right pi regular. So here is one theorem proved by Drazen long back in the beginning of the last century. Given any element A of ring A has Drazen inverse in A if and only if A is strongly pi regular in A. Further, it is noted by Drazen that in a ring A whose nilpotent elements have bounded index, then every pi regular element has Drazen inverse. Okay, in such a case, left index and right index are same. We say A is core element if A belongs to A square, A intersection A square. So A is in both left and right ideals generated by A square. The element A is pi regular if there exists an integer k such that a to the power k is regular. So here is a theorem in the context of associative ring. For a non-nilpotent element A belongs to the ring, the following statements are equivalent. Drazen inverse exists, that is the first case, and the second one is A has a decomposition. A is equal to B plus C satisfying these three conditions. B is of index 1, the first element is the core element, we say, and C is a nilpotent with index D for some integer D. Then whether it responds to pen also?
I am doing.
You are doing. You don't do.
Okay.
Okay.
It is not visible in
behind. Still, it is moving.
It's not visible very well in the videos.
Don't worry. Okay. And BC is equal to CB is equal to 0. Then potency index of C in the above decomposition is same as that of Drazen index of A. Okay, you can go on. Earlier I used to get confused because of its movement.
In the video, it is not visible.
Okay. In the absence of Drazen inverse, our natural attention is to look for right pi inverse or left pi inverse to replace the notion of index of A by right index or left index. For convenience, an element A with right index 1 is called a right core element. Similarly, if left index is 1, then it is called left core element. So we have some generalization here. Given an element A in an associative ring A is equal to B plus C is called right core nilpotent decomposition if the following holds. B is a right core nilpotent element, core element. C is a nilpotent element, and CB is equal to 0. I'm not insisting BC to be 0 here. the notion of left core nilpotent decomposition is similarly defined. Though we focus our discussion in this section on relating right pi regular elements with its right core nilpotent decomposition, analog result and discussions are established with the reference to left pi regular elements and left core nilpotent decomposition. With reference to theorem 7 earlier, which relates Grass inverse and core nilpotent decomposition, one may anticipate that a strong relation between right pi inverse of A and the right core nilpotent decomposition of A. But it is not it is not assured much. We require some more additional conditions, which we'll come to know later. Now consider this lemma that A be an element in a ring A with the right core nilpotent decomposition. A is equal to B plus C with the index of B is 1 and C is nilpotent and CB is equal to 0. Okay. Then A is right pi regular. Okay. Here proof is in the time is going on. Okay. Let me describe proof one short. For A belongs to A, consider the right core nilpotent decomposition. Okay. So that is A is equal to B plus C such that B is equal to B square Z for some Z, CB is equal to 0 and C to the power D is equal to 0 for some integer D. Okay. In such a case, using this property B is equal to B square Z and CB is equal to 0, we can write A to the power D. Okay. That is equal to B into B to the power D minus 1 plus B to the power D minus 1 D minus 2 into C and so on. That implies A to the power D belongs to dA because A to the power D is D into something. Okay. And A to the power D A, the right ideal, is contained in right ideal generated by D. Since CB is equal to 0 and index of B is equal to 1, there exists such that B is equal to B square Z. Now, take use of the earlier property of B and C, its relation with the C. We get by substitution B is equal to B square Z as it is from there. That is equal to ABZ. Okay, so that is equal to A to the power D, B, Z to the power D, and continue to get that is same as that of A to the power D plus 1, Z A to the power D plus 1. So what does that mean? That means A to the power D belongs to A to the power D A. You already seen that B belongs to A to the power D A. So that is equal to BA, and these elements are part of this A to the power D plus 1 into B. Therefore, A to the power D is equal to A to the power D plus 1 Y. Now, from the definition, what do we get? This A is right pi regular. So the lemma is true. But converse is not guaranteed. If A is equal to B plus C is a right core nilpotent decomposition of A as given in the earlier lemma, eta of C denotes nilpotency of C, then index of A, the right index of A is always less than or equal to the nilpotency index of C. That is easy to prove. I'm not going to that particular proof. In fact, the converse part of the earlier lemma doesn't appear to be true, and the condition of A is right pi regular is weaker. So that's why we like to have very stronger condition. Okay. This theorem says that if A is A has a right core nilpotent decomposition, A is equal to B plus C, satisfying those routine conditions. Index of B is equal to 1, CB is equal to 0, and C to the power D is equal to 0 for D greater than 1. If D is equal to 1, that is the trivial case. That's what I told earlier. Then there is, A is a right pi regular, and there exists, in addition to that, there exists beta such that A to the power D into beta into A to the power D minus 1 is equal to A to the power D. Okay. Now, still I like to make use. If a to the power d has generalized inverse, or if I say it is regular, then we can have generalized inverse of a to the power d minus 1. So this trivially holds. Okay. So this is a context where there is no generalized inverse for a to the power d minus 1. Okay. Here in this case, we will have a minus a to the power d gamma to the power k, that is equal to a to the power k, a to the power d gamma a to the power k minus 1. For all k greater than 1, then you take specific k is equal to d. In fact, that happens to be 0. You can see that. So that proves that a to the power d is equal to a to the power d gamma a to the power d minus 1 as we require. Okay. So as a corollary, we have this one. Now, whenever there is right core nilpotent decomposition, then it need not be unique. Then we like to characterize that decomposition. So here, consider a set of all p such that a is equal to b plus c is right core nilpotent decomposition that happen to be subset of a to the power beta, where beta satisfying this condition, a to the power d beta a to the power d minus 1, that is equal to a to the power d, and d is nilpotency index of that particular c. Okay. So this gives us this particular theorem. Let A be a right pi-regular element in A with the right index of A is equal to K, with beta belongs to A, ring A, such that a to the power K into beta a to the power K minus 1 is equal to a to the power K. Then A has a right core nilpotent decomposition A is equal to B plus C, such that B is the right core element, CB is equal to 0, and C is nilpotent with its index, nilpotency index D. So further, the eta of C, nilpotency index of C, is less than or equal to right index of A, and we get this inequality, that is the reverse of the earlier one, whatever we have seen, a to the power d beta, such that a to the power k beta to the power beta into a to the power k minus 1 is equal to a to the power k. K is right index of A, that is subset of D, where this D gives right core nilpotent decomposition. Okay. So I'm not going through on these steps. Let's save some time. And now we have the characterization. Given an associative ring and an element A belongs to A, the following statements are equivalent. The first one is A is a right pi-regular element, okay, with the right index D, and additional condition a to the power d beta a to the power d minus 1, that is equal to D. The second one is A has right core nilpotent decomposition. Okay, A is equal to B plus C with the standard properties what we discussed. In fact, in such a case, that of all such right core nilpotent decomposition is given by this particular set, a to the power d into beta, where beta satisfies this condition, a to the power d beta a to the power d minus 1 is equal to a to the power. As I said earlier, if a to the power d minus 1 has d inverse or it is regular, then these two sets are same. In a regular where every element has generalized inverse, in that case, this trivially holds. You don't have to take these conditions separately. So A is right pi-regular element if and only if it has this right core nilpotent decomposition. Okay, these are the same thing what I said just now. Okay, so these are the references that I consider. These are very old papers, the 50s of earlier century. That's where pi-regular elements introduced. In fact, the concept of regular elements also simultaneously got developed, and there are some more references. This one is also quite old, belongs to the 50s. work related to that particular inverse, which earlier he called it as pseudo inverse, and later it is named as a Drazen inverse. So okay, I welcome you for next December conference also, where we'll be having some set of people interested in linear algebra, of course, algebra, and also matrix methods in various other fields like linear models, where matrix theory is much more, and also graph theory. Okay, thanks a lot. Thank you.
We have 2-3 minutes for questions. If you have any questions, you can ask.
I have one query. Whatever decomposition you have shown, A equal to B plus C, is it unique?
The right coordinate decomposition?
Yes.
No, here I have characterized. It is given by this big set. You get a number of beta satisfying this condition, you get that many. This B is characterized by this a to the power D into beta. If a to the power beta is not unique, then it can't. Drazen inverse case is unique.
The decomposition should be unique.
When the Drazen inverse exists.
Otherwise,
No. It is characterized by.
right by Richter, right. For non-complete.
Oh, this is just associative. I don't even expect identity to be there. Yes.
Commutative would not be necessary.
Yeah. No commutative, not even one identity is not there. It is just an associative.
One is the generalization of the other, or all are independent. Suppose you take commutative, all will coincide something like that, or
These things? No, these are all different. In the context of matrices, generalized inverse is with the rank more than that of rank of A. There are plenty, infinitely many, and these are all with the rank strictly lesser than or equal to that. And group inverse is very special case. Okay, it commutes also. So these are all different. It is not one is special case of the other.
coincide.
Oh, of course, in invertible matrix case, these are all same. If element is invertible, there is no generalized inverse or outer inverse, and it happens. Outer inverse still can be there, okay, because it is a smaller element with reference to minus partial order. But other generalized inverse and these things, okay, Drazen inverse again it is going to be inverse. Okay? They coincide. Group inverse, Drazen inverse, and generalized inverse they coincide whenever element is invertible. But outer inverse are plenty, and it could be lesser than the smaller than. Thank you. Thank you, sir. Thank you. Yes.
So, good morning, everyone. Till now, we didn't get any communication from the first speaker. So we will take a tea break now, and then we will start the next session by 10:45 by Dr. Sam Johnson, sir.
Hello. 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 Mic check. Hello. Hello.
A very good morning to everyone. Our next esteemed speaker is Dr. P. Sam Johnson. Sir is currently working as an associate professor in the Department of Mathematics at NIT Surat. Sir did his PhD from Algappa University in the year 2005. Sir has research interest in the field of functional analysis and operator theory. Sir has more than 30 research publications in the Journal of International Repute. Recently, Sir received Sarab TARE Fellowship jointly with Dr. Hari Krishnan from MIT Manipal. And the topic of the project is a study on frames for operators in Hilbert spaces. Sir has already completed 3 projects under NBHM, DST, and NIT Surat. Now I would like to invite Sir for his talk. Over to you, sir.
Yes. Thank you, madam, so for giving this introduction. Good morning to all. First of all, I would like to thank the organizing committee members, especially the convener of this conference. So Dr. Hari Krishnan PK, the dynamic person. I have to get energy from him for organizing such events. I have to thank the entire team. So they are also collaborating very well. A team has been already set up in this institute. I thank you. I thank all the members once again. Thank you, sir. So the title of my talk is Douglas factorization theorem. So I'm planning to give the Douglas original version of this theorem, which he published in Proceedings of American Mathematical Society. So where he proved a result by considering 2 bounded operators on Hilbert spaces. So before going into this result, I'm going to start with some simple notions for matrices. I'm told that there are some PG students attending. If you're not able to follow these operators, you can just think of matrices. So most of the results in operator settings are basically generalized from the metric settings. In fact, basically generalized from the 2-dimensional structure. Now I consider 2 matrices, A and B. So the 2 matrices have same number of columns. So now I consider an operator equation, X is XB. A and B are known, so X is unknown. So the question is whether this operator equation is solvable. So can we find an X, a matrix X, satisfying this equation 1? Suppose this X exists, then we have equal number of columns. Therefore, you can look at the corresponding rows, so they will be in the same space. Therefore, one can easily understand that this row space is a subset of row space of B. So you know what is row space? The space generated by the rows of the matrix. So if you find any difficulty, maybe you can start from right side, because most of the operator equation, we will look at the columns. So because the columns space of a matrix is nothing but range of an operator. So maybe we'll start with the operator equation 2 if you find difficulty in operator equation 1. So 2 matrices with equal number of rows. Therefore, if you look at each column, it is in the same space. Okay, so therefore, this operator equation has a solution if and only if the column space of A is a subset of column space of B. So both sides it is clear. Suppose if 2 is true, then column space of A is a subset of column space of B. What do you mean by column space of A? Collect all AX, X is varying. So this AX is nothing but all AX, X is varying. And this is same as collect all BXY. This is X is varying. This is nothing but B of YX. Therefore, it is in the column space of B. So one implication is clear. But the other implication is also true. But we have to find the corresponding matrix B. What is B? So we are given with column space of A is a subset of column space of B. So therefore, every column of A is a linear combination of columns of B. So therefore, we can write as a linear combination. Therefore, you have some weights, you have some scalars. This scalar will give the first column of Y, because you know the matrix multiplication can happen in many ways. You can write row wise, you can write columns, you can write entries. So here we are writing the product by in terms of columns. The columns, each column is nothing but the linear combination of columns of B. So therefore, that weights can be taken, you can get Y. So if this is understood, then the operator equation 1 is clear, because this time X is on this side. So we can say A is a left multiple of P. If this is satisfied, then I can say A is a left multiple of P, and the equation 2 is satisfied, then I can say A is a right multiple of P. So mathematicians are having habits of generalizing everything. I don't know whether all of them are good, all of them are bad, I don't know. But as far as I'm concerned, if generalized ones are useful, then it is good. Just for the sake of generalizing, one should not do this. If it has some application, so then there is a meaning for generalization. So now this question one can ask for operators. So if A and B are operators, because the next simple structure one can think of for operators on Hilbert space. Operators on Hilbert spaces. Suppose if I consider A from a Hilbert space to itself, B is also from the operator on the Hilbert space H, then can we have these results? So if you look at this result, there is no analysis. So you have only algebra. So inclusion relations, this is inclusion relation. The top one is an equation, solution. We have no condition on X and Y. So if you are expecting, if you are starting with bounded operators, then the question comes whether we get a bounded operator X, whether can we get the bounded operator Y satisfying these two equations. So it really matters. So now I'm going to consider only 3 notions. So 3 meals in a day, therefore you can think of 3 notions for this presentation. Assuming that today is maybe 3 days for the conference, okay, like 3. So 3 notions are taken. You no need to know any other difficult notions, only these 3 notions. These 3 notions we will discuss first. Then we will discuss the equivalency of these 3 notions. The first notion, which is range inclusion. So now I have a structure, a topological structure. I consider Banach spaces, and there are norms on each spaces. Therefore, we can discuss the topological properties of it. So now I consider 2 maps, 2 operators, and these 2 operators have same codomain. If you look at it, this Y is same. So therefore, when we have an operator, there are several subspaces exist. So 2 of them, many of them, many of you know the subspaces. One is null space, other one is a range space. Therefore, these ranges are there in Y, range of S and range of T. So if they are comparable, then this is the first notion, range inclusion. So one may be smaller or equal, many conditions are there. Therefore, if these ranges are comparable, so then we call as a range inclusion between the 2 operators. This is the first notion. The second notion, which is a majorization. If you look at here, the domains are same. Domains are same, X, X. So therefore, when we have Sx and Tx, X is varying over X. If there is an M satisfying this inequality for all X, then we can say T majorizes yes. Something is dominating, we can say in some sense. So T is majorizing yes, or S is majorized by T. So when we have this inequality, there are several observations. Simple observation is, suppose Tx 0. So X is in null space of T. Obviously, X will be in null space of S if the inequality is satisfied. Therefore, we can say if T majorizes yes, And majorizing operator will have a smaller null space. So it becomes smaller and smaller. This is the second notion, majorization. There are some observations about this notion. So it is analytical in nature. So you have norm, you have inequality. You can discuss operator between these two subspaces. Suppose one particular operator is fixed, which is t from x to y. There are two operators s1 and s2, which are majorized by t. So then obviously the sum is also majorized by t. So you can get the inequality relation, because the sum of a linear operator is saying a linear operator, and you have triangle inequality for the norm. So therefore, excuse me, this is valid. And then any arbitrary operator is taken, then we can multiply on left side, then that is also majorized by t. If the S is majorized by t, then R is also majorized by t. So therefore, you will, when these two are there, then immediately we will get the notion called ideal. Ideal. So now assuming that all spaces are same, so in BH, X is a Banach space B of X. Now one operator is fixed. We are collecting all operators which are majorized by t, so it forms a left ideal of B of X. So there are many interesting results we observe. So I don't want to tell them. So this is a collection which forms an ideal. So you know, this set of compact operators is an ideal, which is a closed ideal. So this plays an important role with respect to one particular operator t. And this is also transitive property. So if t majorizes yes, S majorizes R, then t majorizes R. So this you can observe from the inequality relation. So remember, whenever majorization notion is said, you can see in terms of inequality. And what is the characterization for a closed operator, closed range operator? Because whenever we are solving an operator equation, Tx is equal to y. Suppose if y is in the range of t, then we have a solution, but there could be many. So now we want to find out some solution which has some additional property. So you have plenty of solutions. You may have a confusion which one has to be chosen. Maybe you can choose a one which is near the origin or smallest num, those things. Therefore, where you require the closeness of an operator. So here comes a characterization for a closed range. So here x and y are Banach spaces. An operator has a closed range. A range of t is closed. Then there exists a positive number m in which this inequality is satisfied. So q of x is a quotient operator, because when we have an operator which is not injective, when we change a domain from the space to its quotient space, then the operator can be made into an injective map. So basically, we apply open mapping theorem or bounded inverse theorem to get this other inequality. So this proves that the range of t is closed, then t majorizes its own the quotient operator. If this happens, this is a characterization for a closed range in terms of the new notion majorization. And in general, one may ask, suppose there is a relation between two operators S and T. Suppose one is majorizing other. One operator has some property. So we are expecting that whether other operator is also having the same property. So this has been analyzed, studied by many mathematicians. We have also done with respect to closed range operators. And here I wish to tell some simple results one can expect from this. Suppose T majorizes yes. So what do you mean by majorizes yes? Norm of Sx is less than, there exists a positive number m greater than 0, such that norm of Sx is less than or equal to norm of Tx for all x in x. Then this condition is written here. Sorry, here it's written. Suppose S has a closed range. This is not enough. So to talk about the closeness of range of T, but these two operators will have same null spaces, then range of T is also closed. And the compactness one can observe easily. So this is a consequence of a relation one can expect from the majorization. What something is available for one operator, and you have a relation between them. So we are expecting the same thing for the other operator. So this third notion, which is a factorization. So we have two operators. and these two operators have same domain X. And if there is an operator V, which is a bounded operator V, in which this S is factored as a product of T with some other operator, we call S is a lift multiple of T. Then this characterization is useful when we go for it. So that's what I started with the metric settings. So the column space, row space. Similarly, if there is another operator U, this time the corresponding range spaces are same. Your domains are same, your codomains are same. If codomains are same, then we can expect an operator U in which this happens. Then we say S is a right multiple of T. So you can factor one operator. You are given with two operators, S and T. We are interested to know the factorization of one in terms of other with the help of some bounded operator. If you have a common domain or common codomain, so we are interested to know whether this factorization is possible or not. Okay, so Douglas theorem, I'm going to state this theorem. So he found this relations among these three notions. Basically, he discovered these relations in the study of an unpublished manuscript of D. Branches Raunak. And then this paper got published in the Proceeding of American Mathematical Society. And he has found the relation between these three notions. So I'm going to tell you the statement. The idea is to discuss this result and then applications of these results in different research areas. So my intention is to give this theorem, which has three notions. I may give a full proof for bounded operator on Hilbert space. So I will only state the results for bounded operators on Banach space. Then I will simply give a statement for this and several other generalization of this. Okay, what is the result? This is a result. A and B are bounded operators on Hilbert spaces. So remember, one can also extend this. This is he himself has done it, but the proof is same only. Therefore, in order to minimize this notation confusion, I have considered operators from H2 itself. But the same trick one can follow so that you will have a same codomain H in which ranges are compared. So two operators are there, A and B. They are bounded. So bounded operators are nice enough to handle. And this following three notions are equivalent. The first notion is nothing but range inclusion. Range of A is a subspace of range of B. And then second notion I said, which is a majorization notion. So here B star majorizes A star, B star, not B. B star majorizes A star. And there is a bounded operator C in which A is equal to BC. Which means we can factor A in terms of B in which B is a right multiple of B. So proof is simple. If you have 3, you can get 1. It is not a problem. If you have 3, 3 implies 1 is simple. 3 implies 1 is simple because if you have AX is nothing but BCX, BCX nothing but B of CX, therefore it is in B. So similarly, if you have 1, you will get 2 also. You will get 2, but we have to define an operator. We have to define an operator. So that notion it is difficult. So you can get 3 from 3 to 1 and 3 to 2. It is not a problem. It is easy. But what is an advantage of this inequality? There are several advantages of this inequality. Whenever you have this condition, definitely you can think of some map. You can think of some map A, maybe I'll call S, from, suppose this inequality is true. Then you can define a map from range of B star to range of A star. So how the elements are sent? The elements are sent from B star of X, because every element in range of B star is of the form B star of X. So B star of X goes to A star of X. So because of this inequality, this S is bounded. So this plays a crucial role in defining this operator C. So therefore, constructing an operator C, it is direct from this inequality. And when you have these assumptions, for example, 1 implies 3. Suppose I have 1. So how do I consider this C? how do I define C? So just now I proved 2 implies 3. We can get yes. So then we take the adjoint of this, then we can get nothing. That is nothing but C. Similarly, one can prove 1 implies 3 also. Whenever any element is taken, we have to define a map. So that is of the form AX. AX is there in BX, so therefore it will be in some BY. So, but that need not be unique. But if you restrict it to its null space of B per, then element is unique. Therefore, for each X, you have an element in N of B per. So which way, that is the way in which C is defined. So what I'm saying is, C sends an element X to an element Y. Where is Y? Y is in N of B per, which is coming from the first inclusion relations. Though it is a simple proof, but this is a result which gives a connection between these 3 notions. Okay, so that I was telling in the beginning, so he himself has extended by assuming the codomain is same, then these 3 notions are same. The same proof only, the proof is exactly the same. So, but we should be careful with the notions where elements have to be taken. So now the question comes, whether we have defined this notion for operator, what can we say about this adjoint? Because adjoint also an operator on H, because H is a Hilbert space. So therefore, we have 2 types of multiples. A is a right multiple of B, and A is a left multiple of B. Because you, maybe a simple example, if you have a matrix A, real matrix A, then if you have, then A star is nothing but transpose of this. A transpose A star is nothing but transpose of the matrix. Then the column space of A is same as the row space of A star. Therefore, in the beginning, I was telling the row space of a matrix, therefore, which is nothing but the column space of A star. That is done here. That is done here. So therefore, we have got 2 matrices B. Here, A is a left multiple of B. Here, A is a right multiple of B. So this results are equal. This all notions are equivalent. So we can compare the ranges of 2 operators or the ranges of 2 adjoints of these operators. So immediate question comes whether this result is true for Banach space settings, because there are so many things available for Hilbert space settings. Every closed subspace is complemented, and then the dual of Hilbert space is itself. But now we would like to see whether this result is true for Banach space settings. And beginning, I don't know whether Douglas did not try. I don't know, because he did not give any elaborative proof for Banach space settings. He was trying to take this same settings, same equivalent conditions, and then he was trying to find the relations among these 3 notions. And then some relations are not true. He was trying to find some counter examples, and then he was referring some other mathematician unpublished work, and then he gave several examples. But in later, a mathematician, Mary Embry, she observed very interesting thing among the operators on Banach space. She said instead of applying the range inclusion condition for operator, why can't we apply it for its adjoint? Because if X and Y are Banach spaces, you have an operator T, then the adjoint T star goes from the adjoint of Y to adjoint of X. It is not again going from between X and Y. So therefore, this is different. So this simple observation is excellent, and she was able to give this result. So this result is a generalization of this result in that particular setting. Therefore, A and B are bounded operators on a Banach space X. Instead of comparing its ranges, now we are comparing its adjoints. Now these 3 notions are equal. So remember, there is an interesting observation here. So we are not able to extend. We are not able to extend this operator because every subspace need not be complemented. Even it is closed on a Banach space, every closed subspace need not be complemented. Complemented one you get as a free. So every closed subspace of Hilbert space is complemented. But here it is not true. Therefore, these settings are different, but still all 3 notions are equivalent. So the problem was open for many years, and people are trying to find the relations among these three notions. And one simple change is here. When you want to compare its ranges, so we have started with A star, therefore we cannot have an element in H1 because the space is different, because X and Y are Banach spaces. So therefore A star basically goes from Y star to X star. If we have A from X to Y, so A star goes from Y star to X star. Therefore, this second condition had to be redefined. So still this is true, and some results are obvious. So 3 implies 1, 3 implies 2 are obvious. With some difficulty, one can prove 1 implies true. 1 implies true. You have to believe me. So these are the true results. And mathematicians gave several examples. And Douglas in his unpublished manuscript, he gave a counter example, which appear in the paper of Embry. And then he proved this relation is not true. And there are so many mathematicians started giving examples. With some conditions, the results are true. What are those conditions? N of B is complemented. N of B, because for any bounded operator, the null space is always closed. So if it is complemented, then this is true. And the Banach space Z is reflexive. So the double dual, the second dual is the space, then the other relation also true. So if both are assumed, then we have one more implication. So there are 6 implications. 3 of them are true directly without any assumptions, and 3 of them are true with some conditions. But for your information, these details are not necessary. So N of B is complemented, that is redundant, it is freely available, and every Hilbert space is reflexive. Therefore, these 2 conditions are not necessary in a Hilbert space settings. But with these assumptions, the results are true. Therefore, you must have observed in many papers, if people are working on Banach spaces, they will try to assume the reflexivity property, which is powerful, and also this best approximation property or the complemented property. And Douglas in his paper, he gave results for unbounded operators, because dealing unbounded operators, it is not easy in general, but closed densely defined operator is nice enough because of densely defined. So its adjoint exists. Because of closeness, we can expect many results for bounded operators, which are also valid for this class of operators. This is a very well studied operators. So I'm not going to tell these results, but these 3 notions are not equivalent. So one implies others. For example, the first one, majorization gives the factorization. You know this notation. This is very much available for unbounded operators. This is a restriction. The restriction of B to the domain of A, you get A. So this was given by Douglas in 1966. And there are several generalizations of Douglas theorem. And now people are working for unbounded operators on Banach spaces, and then regular operators on Hilbert C-star models. So this notion is nowadays very popular. This result also very much popular. There are several consequences of this Douglas theorem, and operator theoretic approach one can have. And then if you are perturbing an operator with respect to some other operator, then we are expecting the resultant operator will be also in the class. And then in the class of existence of more windows of operators. And then we have used this Douglas theorem for operators with closed range. So there are several consequences. I would like to tell you 3 of them with our work. So let me start with a simple definition of EP matrix. So you may have I take a square matrix A, I just transpose. If the corresponding the column space are same, then we say the column space of A is same as column space of A transpose. Then we say a matrix is EP, equal projection matrix. So this is very well studied by linear algebraists, and our Manjunath Prasad also has done a lot of work in this field. Now this notion was extended to operator settings, but we require a closeness. So when the ranges of A and A star are same, then we say the equal projection operator, EP operator, but we require closeness because this notion is equivalent to the commutative property with respect to the Moore-Penrose inverse. We are expecting this. This is also an equivalent. In order to have this Moore-Penrose inverse, we need to have the close rangeness of A. So for this notion, we define for closed densely defined operators on Hilbert spaces. We could extend some of the results from bounded settings to unbounded settings, and in which the Douglas theorem we have extensively used. So repeatedly used in many of the characterizations. And these are the two papers. One is on closed EP and hypo EP operators on Hilbert spaces. Other one is on product and factorization of hypo EP operators. So hypo EP it is simple. So you have range of A is a subset of range of A star. Range of A star. Again, a close rangeness is needed. So this is this has more collections than EP operator. This is a second consequence. The second applications we have used Douglas theorem very well. There is a notion called frame for a Hilbert space. In finite dimensional case, this frame is very much useful, applicable in many different disciplines. And this is a collection of all sequence. This is a sequence. It may be finite or infinite. So suppose I assume H is an infinite dimensional space. So it is a sequence. If there are two constants A and B in which these inequalities are satisfied, then we say this is a frame. Because orthonormal basis, if we have an orthonormal basis, then we have a equivalence relation. Every element we can write X, E, and En. Because what is an advantage of this notion? I know every element will be able to write as a linear combination. But the question is, how do we find the scalars? The scalars one can find with the help of the basis itself. So that for a higher dimension space, finding scalars is not easy. So, but when you have an orthonormal basis, it is a frame. But the frame is a little generalization of this orthonormal basis. You don't need to have equality. You have inequalities on both sides. So each frame gives three operators: analysis operator, frame operator, synthesis operator. So frame operator is a composition of these first two operators. Therefore, one can discuss some results. One can apply operator theoretic results in order to get results in frame. And we have used Douglas theorem in these two papers. So the first paper on frame operators on K frames, because K frames is one of the generalization of frames. There are so many generalizations, but with the help of a bounded operator, one can have this new generalization. And then we have also used this Douglas theorem for factorable weak operator value frames. So these two works are related to frame theory. And this is the last and final applications of Douglas theorem in dilation theory. Suppose you are given with something, you know very well, several interesting results are available on a vector space with complex field. Suppose I would like to know these results for real field. Basically, we will do the complexification of the space and operators, and analyze or get the results from the complex analysis techniques. Then we restrict to real case. The same thing is there for in dilation theory also. Suppose one operator is given. So we would like to see this operator as a part of some very well understood operator. So this self-adjoint, unitary, those operators are very well studied. Then for any given operator, we would like to see as a part of this. So it has been given by Halmos in his paper. He started this research area. He analyzed for a contraction map. If any contraction map is given, then how do we see as a part of a unitary operator? So, but we have done it for a dilation of linear maps on vector spaces. We have extended partially the work of Professor Rajaram Bhatt from ISI Bangalore. He has written a book on dilation theory, and this work is also related and some consequence of Douglas theorem. And there are, I would like to end with the references. So these are all main references. This is the first paper. given by Douglas. It appeared in 1966. And Embry improved his results from Hilbert space settings to Banach space settings. And then Barnes contributed a lot. So he analyzed the implications, the three implications with some conditions. And Bowlin found some examples, counterexamples, to state that some implications are not true. So with this, I'll end my talk. Thank you all. Examples one can generate, sir. So what you are asking is, suppose a T majorizes yes. So we have, there exists a constant m greater than 0, such that norm of Tx, norm of Sx is less than or equal to m times of norm of Tx. So for all x. So one thing is simple. We can take any operator and multiple of that, and corresponding m will be the norm of that, one way. So therefore, many ways we can have. But if we are having this, then we have that part also. This is even only. So starting with any two, and the third operator of your convenience, that will decide the norm of this, that will decide the value of m. Yes, sir.
If we replace this as T is like a subjoint,
Yes, sir.
then that M hyponormal.
M hyponormal, where sir is working on M hypo. Yes, several. Yes. That are all examples. Yes. Yes, sir. You're right. Yes. And basically, this is analysis. So only ranges are compared. So ranges of A star, EP, hypo, EP, those things. If you have some analytical notions, which is also comparing its length, therefore, which is much stronger. Yes.
The inverse, consider the inverse of an operator. So is T majors is, so what about the inverse?
Yes, inverse. So what you are saying, T majorizes, yes. Suppose S inverse exists.
Yeah, S inverse and T inverse both exist.
Okay. Okay. So now we have to start with, because any identity operator we can split into T star in a convenient way. Yes, S inverse. So we can apply this inequality wherever you require, because this is also same as S inverse S and T inverse T. Wherever we have this inequality, so therefore that element can be operated upon. So I do not have results, but one can try here. So starting with norm x, which is Ix. So we have T inverse or T inverse Tx. So any of T inverse is bounded, then it comes out, then something can be said. Otherwise, starting with T inverse. But I do not have an answer right now, but one can find. But still, there are many interesting problems one can think of as are asked such question. Suppose T majorizes yes. So what about T star majorizes S star? T inverse majorizes S stars, those things. But we have to deal with only inequality. Yes. Okay, thank you, madam. Thank you all. No, stop. Okay, thank you.
such as matrix by DST CSCRP and minor research project by University of Calicut. So I request now Dr. Prasad to continue. Thank you.
Thank you, Dr. M. Kundar, sir. And I thank you for the organizers for inviting me for this conference. And I thank MIT Manipal for the hospitality, and this conference is arranged in a very nice and net way. Thank you. And am I audible? Now today my topic is generalization of T hypernormal and some results related to invariant subspaces. And because some master's degree students, I just start with what is invariant subspace, but what is the problem? And the space axis the subspace. And consider continuous linear transformation x to x. And if you take M is a closed subspace of x, and then M is said to be invariant under T if T of x
that is being which is being
if x is finite dimensional vector space, then definitely we know that it has eigenvectors that gives the consequence of fundamental theorem of algebra, and so we can generate that eigenvector, eigenspace, and so that eigenspace will as an invariant subspace of case of finite dimensional. If it is infinite dimensional, then n pro in any case is 80. To give a example that shows that in the NAP space setting, this problem has negative answer. To give an example and prove that example does not have invariant subspace in the NAP space. And so now we start our talk. And as usual, H is infinite dimensional complex space, and VFX stands for algebra of bounded linear operators. And this is the problem, certain standing problem. Because every bounded linear operator on an infinite dimensional separable complex Hilbert case non-trivial closed invariant subspace or no. And this is we have a lot of positive answer in this area. If T is normal, that normal means T commute with T star. Then we can say for this type of operator, it has invariant subspace. The famous theorem of spectral theorem for this normal operator is invariant subspace for this type of operator. For compact operators, and we know that very well known theorem of Lomonosov gives a positive answer for this invariant subspace for compact operators. Now we check, we try to add this more classes of operators in this gallery of operators that satisfy invariance. And the talk is split into two sides. First, I am going to introduce one new class of operators. Then next, I will discuss how what are the conditions to get invariant subspace for that operator. And we start with a hypernormal operator. And an operator T is hypernormal if it satisfies this inequality. T star is less than or equal to T star. And in this hypernormal operator has been studied by many eminent persons, like Harmos, Putnam, Stamford, Putnam, CI, etc. And the aim of this talk is to give an introduction to the class WAST operator is defined by me and one of my collaborators, Professor Tanahashi, and we speak about the existence of invariant subset for this concept. And this talk is based on some of my articles related to this area, and especially this article and this article. It gives some relation to the invariance of this problem. Okay. And to introduce P hypernormal PWAST operator, we need some two famous inequalities. One is Lohner-Heinz inequality, and another one is Rootine inequality. If A is greater than B, then we can say that if P is like between 0 to 1, then we can increase the power. Okay. This Rootine inequality is actually the generalization of this Lohner-Heinz inequality. If you assume that R is equal to 0, then what happens? If R is equal to 0, then from this inequality, you can find this 0 less than P by Q less than 1, and so P raised to P by Q greater than or equal to B raised to P by Q. So from this point, we can understand this Rootine inequality is a generalization of Lohner-Heinz inequality, and you can define by using the Lohner-Heinz inequality, you can define P hypernormal, because if T is hypernormal, that means T star T is greater than or equal to T star. This is the definition of hypernormal. Suppose this is A and this is B, and if T is between 0 to 1, then we can price the power by using this Lohner-Heinz inequality. So this is the new class of operator P hypernormal, and it is defined by Aldrich in 1990, the journal Interpretations and Operator. And it is very interesting to see that this if Q less than P, that P hypernormal implies Q high. That means if Q decreases, our class increases. So that means if I take that P star T or Q, that you can write it as P star T or T whole power Q by P. But if you assume that T is P hypernormal, then you can write it as T star or P Q by P. That is P is Q. So P hypernormality implies Q hypernormality even if Q less than. Yeah, in the same paper, Aldrich observed that if you take P hypernormal and where P is like between 0 to 1 by 2, then this type of inequality is satisfied. This means
I'll
T
be-
tilde T cap, the tangential transformation is some T plus 1 by 2 hypernormal. So if we are adding 1 by 2, that means Q that is more than T. So this class is decreasing. If if P increases, then class decreases. Actually, then what is the ultimate aim? This P hypernormal is a big class, and it transforms that P hypernormal into a smaller class and study this bigger class by using this algebraic transformation. Because this algebraic transformation shares many properties. For example, spectral point spectrum, ion spectrum. These are all same for P and P cap. So it is very easy to find out the biggest class by using the algebraic transformation. If some properties happening in smaller class, then if you have algebraic transformation, then you can make it convenient to work the higher class. That is the idea of algebra. And after his definition, with Fruta and Yoshino, they define the generalized version of algebraic transformation. If that is represented as T as T6 or T power 2 or T or T for S and here or greater than 0. Yeah. And in the same paper by Fruta and Yoshino, they observed that if T is T hypernormal, then this satisfies this particular inequality. And this inequality is used to define a new other class that is named as class WASC. If T satisfies class WASC, if this two inequality satisfies, it is defined by Ito in 1980. Actually, the inclusion relation is every T hypernormal is contained in class W. And every hypernormal contained in P hypernormal. This is the inclusion relation among this new class of operators. And this is one of the striking research by Yamasaki, published in Integral Equations and Operator Theory in 2002. That this if this inequality satisfies, then it implies the other inequality. That means, you suppose if this inequality satisfies, then we call this that type of operator is class AST. And then his observation is, if one inequality satisfies, then that implies other inequality. That means ultimately this class of coincident, that class AST and the WAST coincide. In 2014, and we generalized that class WASD and we define class PWASD operator. And nothing with that, we just utilize the lower Hens inequality. And we have the previous step, we have this is W class ASD, just increase the power by lower Hens inequality. Okay. This is the definition of class PWASD. And very interesting to note that if T is T class WASD, then T, that is the generalized algebraic transformation, is P rho by S plus T hypernormal. So this class PWASD is the biggest class that includes hypernormal, P hypernormal, AST, etc. And now we have a linear transformation that maps from this biggest class to the smallest two. T to the AST is P by P rho by T hypernormal operator. And there are some basic observations for this process of operator. If P1 less than P2 and F2 is less than F1, then the T2 is less than T1, then T2A WAS S2 T2 is half T. That is the inclusion relation. If S1 increases and if S2 is less than S1 and T2 is less than T1, then T2 cross WAS S2 T2 is T1 WAS S1 T1. That is the inclusion relation. What happens if that depends the value of S1 and S2. And also we observe that if T is cos TWAST, if it is invertible, then T inverse is also cos AST. And if this generalized observed solution, T power S u mod power T is cosinormal, then T is also cosinormal. And operator T is said to be cosinormal if this commute with U mod T commute mod T U. So this T tilde S is cosinormal, and we can prove that T is also cosinormal. If P is cosinormal, then we say that the T coincides with the observed function. That is our T tilde ST is mod T power S, U mod T power T. If T commute with U commute with T, then you can write it as U mod T power S plus T. If S plus T is 1, then it is U mod T, that is T. Okay, so these are some basic properties of this TWAST operator. Then the next one is that mod T is equal to R of T. That means this is normalized, and this one is we proved in 2018 that this is the public portion of PWSU. And now we come to the main section that about the invariance space, and we need some basic partitions of spectrum that a complex number lambda is said to be sigma A of T if there exists a sequence xn of unit vectors such that T minus lambda xn converges to 0, and the next one is about conversion spectrum and joint point spectrum, joint approximate point spectrum, and these two relations we studied recently that if our task is TWAST, then this non-zero point spectrum and a non-zero joint point spectrum coincide, and if T is TWAST, then approximate point spectrum and joint approximate point spectrum are coincide. And these are the some basic ideas we need for the main part. And now we start what happens in the case of TWST about the existence invariance. And we are going to generalize some theorems of Putnam, and Putnam studied in 1974 in transaction of American mathematics and concerning the point spectrum. He proved that if lambda is in the boundary of spectrum of T, then mod lambda belongs to sigma mod T intersection sigma mod T. This notation means that lambda is in the boundary of T. It is for the case of hypernormal operator. And in 1995, that show Huria and he proved the generalized theorem to in the case of T hypernormal operator. That this is in the journal Proceeding American Mathematics. If I am correct, that is in the American Mathematics. In 2018, we extended that result. We give a TW class AST version of that result, and it is published in ICAAA series in 2018. And we proved that if lambda is in non-zero approximate eigenvalue of PWST operator, then mod lambda belongs to sigma mod T intersection sigma mod T star. And by using that result, we can show that if T is a class PWST operator and if S plus T is 1, then there exists a lambda belongs to sigma T such that mod lambda not belongs to such that mod lambda not belongs to the intersection of the spectrum of mod T and spectrum of mod T. Then T has no previous. If this happens, then definitely we can say lambda is in sigma T and this mod is not belongs to this, then definitely this lambda should be in compression spectrum. So range of T minus lambda partial is closed invariance. So in this case, we can set that problem if this condition that this biggest class And we see that if lambda is in the boundary of T, then mod lambda belongs to sigma of mod T intersection sigma T star. And if lambda is in sigma T, that's this mod lambda is sigma. This is the case, the case of T hypernormal operator. This answer is yes, because we told just before that lambda is in sigma A of T and mod lambda belongs to sigma mod T. So this is true for the case of T hypernormal. In general, this is not true. If you take a unilateral shift, then the spectrum is goes to the unit disk, but the T star T is identity, so that is single transit one. So this is not true the case of unilateral shift. If the converse is true for T hypernormal, answer to that question is if T is T hypernormal operator, then sigma mod T is contained in rho sigma T, where rho is mapping from C to R defined by. This is the result by Cho and Ito, published in Proceeding American Mathematical Society in 1990. So this answers the question. This just the converse is true. And what we did, we just give a PW class ASD version of that result, and we proved with the condition sigma T is correct. By using this condition, we can able to answer one more. We can able to give one more condition for the existence of invariant result. If either mod T or mod T star is not connected, then T has non-trivial invariant subspace. This is one way we study the existence of invariant subspace for PW class ASD. Now, this is my the upcoming is my independent part, and two operators S and T are said to be co-similar. If there is a co-T affinities, co-T affinities means that is injective and denser, such that this intervening relation satisfies. This definition is by Nagy and Forrest in 1970, and Duggal in 1998 introduced a condition for T hypernormal operators for non-trivial invariant subspace. We have accepted it is possible to extend this theorem for our T cross WST version. And what is my observation is if we define x equal to like this and y is equal to like this, then by a simple calculation we can able to find the equality these two equality. Okay, but now it is not this x and y are not closely similar, because we have to prove that is injective, and then that we have no proof. Okay, and this is my theorem that if T is pure of PWST, means it is cannot have normal path. Completely T type normal WAST operator. And if S plus T is 1 and T lies between 0 to 1, and 0 is not in the point spectrum of T and has cancelled. These are the this much condition we need to find the invariant subspace problem for this process of the services form. I try to reduce, but right now is still this is the result not able to reduce that. Then T has not the invariant subspace. If and only T till is the T till is the second order transformation. Okay, for this proof, the main idea is this relation. We proved that there is some intervening relation, and the next step we prove that x and y are injective and transferring. So these two are cosine. That is the first idea. Then, if two operators are cosine, if we one has invariance, then there will be one has invariance. That idea was included. So we find the result that with this condition, T has non-trivial invariant subspace. Now, a little bit of functional calculus. An operator is said to be generalized scalar operator. If there is a continuous sigma algebra homomorphism from C naught to M to C, where this C naught m is the set of continuous function in this differentiable of the order m. If this spectral distribution, if an operator has this spectral distribution, then we call that operator is generalized scalar. If an operator is a restriction of generalized scalar to an invariant space, and we call it as a subscalar operator. And in the next theorem, we can observe if this is a relation between the spectrum of T is equal to spectrum of U mod T power S plus T, and this is very highly useful. That is already proved. And the theorem says that if T is a pure classical AST operator, such that 0 naught belongs to sigma T, and T has 10 threads. If spectra of T has non-empty interior, then T has non-interior subspaces. And this result is coming by this relation. For T, you can write it as sigma U mod T power S plus T. That is sigma T tilde S plus T. So, what is our assumption? We are assuming that T has, if the spectra of T has non-empty interior. Now we observe that spectrum of T and spectrum of T tilde are same. So, if T has non-empty interior, the spectrum of T tilde has also non-empty interior. And the other thing, this T tilde, we already observed that this algorithm transformation maps from A plus AST to A rho hypernormal. But here rho hypernormal as is subscalar. That is proved by this chain giving again, and it is published in Proceeding American Mathematical Society. And so now we combine this both idea, and now we can say that this has this is subscalar, and with the dense with the non-empty interior, this operator is invariant. So that is done by Tesla in 1987. So by combining these two ideas, it is easy to show that this our class period ST has non-trivial invariant subspace. But the basic idea behind that is these two operators are co-similar. And this previous result that T has invariant subspace, if and only T will have invariant. Okay, now and this is another version, another application of our main research, and this is Cho and Virian in 2003. They give a P hypernormal version of Nakamura result. Actually, Nakamura was executed the postral and can see the study the conditions for invariant subspace for hypernormal operator. So this Nakamura's result modified that result, and this is and after that in 2003, Cho and Huria they gave a P hypernormal version of this Nakamura. This result says that if T is pure P hypernormal operator, and that T tilde means it is the second algorithm transformation. It has the Cartesian decomposition x2 plus iy2, where x2 and y2 are self-adjoint operators. And if suppose T has non-empty intersection with the open half plane, these two open half planes, and if this integration is finite, then T has non-trivial invariant. This is the result more P hypernormal version of result by Nakamura. And by all the theorem, just we just discussed, and we are using all these things, and finally we are trying to find out one more condition for existence of invariant of PW class A. Yeah, and this notation here, this x2 and y2 self-adjoint operator, and self-adjoint operator has spectral decomposition, and so you can write the integral of. And this ES, what the EX2 means that ES is defined as the water subset of the real line having the largest Lagrange measure and satisfied. This is just what I am writing here, because this x2 and y2 self-adjoint, then you can use this idea of EF x2 and x2. Okay. And before going to our final result, I just give some result we use find out the final result. And this is the one observation that we have here as WASD operator with the dense range, then this T top. That means second first Aldrich transformation is pure Q hypernormal, where Q is P rho, where rho is between 0 to minimum T. And this is another observation. If T is an operator with a kernel, and that T is generalized transformation of T, such that F plus T is equal to 1. If T has cycle vector, then T tilde has cycle vector, and satisfies kernel of T tilde ST is equal to 0. By using these two results, we can able to obtain this result of actually what we have done. We are extended the result of Cho and Korea to TW of AST operator. And here T tilde till second Aldrich transformation of T tilde that acts as a T hypernormal. Actually, we have a big class, P class WAST, and we transfer it into a smaller class, P rho hypernormal operator. And you study already there are many results for this T W T hypernormal. We extended that result through this Aldrich transformation to this biggest class. That is the idea. Okay. Before summing up, and this new class is defined in 2014. Still, it is not completed. There are a lot of things to do. Still, we cannot have a good idea about this class. We have some basic results and around 10 to 12 papers in this class totally. But we need to, because once it started with the hypernormal and P hypernormal, there are a lot of papers in that P hypernormal, etc. But still, we cannot able to get a good structure of that operator. We are trying to find out more results. Now, recently we find out this P class WST, and the importance of this class is it contains all other commonly classes considered class. So as of now, this is the biggest class, and we studying in the biggest class means it is if you find out some result, and it is true for all other classes. And still there are a lot of us to need to get a good idea of this class, and these are some basic questions that we need to try. First one is this is a general question. If give us T is class P WST operator, right now we have T has not trivial invariant surface with some condition. If it is possible to take it out that condition or not, or otherwise, or any other idea to find out non-trivial invariant surface. And the one other question is in integral equations and operator theory, that is allowed studied, not others, that Yamasaki studied if T is cos WAST, then T raised to n is WAS by n, T by n. So we are checking whether it is possible to extend this to our P class WAST or not. This is the last question we need to try, and the final. And I already told that Yamasaki observed that every WAST and the WAST coincide because of this inequality. This is one of the striking results for Yamasaki, that is obviously integral equation and operator theory. And still we don't know, does our class PWAST coincide with PAST or not? Not AST, we can define PAST, and is it this PWAST and PAST are different one from one? If you prove this implication, then we can say that these two classes are coincide. We are trying last 10 years, but I cannot able to solve that. So these are some results to find out some invariance of space for this larger classes. But we are saying we are trying to add some classes of operators in the gallery of classes that already have invariant spaces. They are like normal. Subnormal operator has invariant subspace, and a hypernormal with the thick vector has invariant subspace that is done by Brown, that is published in Annals of Mathematics. Okay, now we have this gallery. People are very less, only 4 or 5. We are trying to have many. Okay, but it's not easy. With some condition, we are getting some results. Okay. We believe that's concluding the lecture. Thank you for your attention.
Hello. I invite if there are any questions from the participants to the speaker, online, offline as well. Please.
The definition of hyponormal operator.
Yes.
If the adjoint is replaced by more Penrose inverse,
Yes.
then this is the definition of hypo-EP.
Hypo-EP.
And we could generalize the Kubler-Putnam theorem.
Okay.
When we replace adjoint by the more Penrose inverse.
Okay. Fagli-Putnam not Fagli-Putnam type.
Type theorem. Yes, correct. Type theorem. So because it's some contingent, because that is for only adjoint. Yeah. Now I would like to know this when you are raising the power.
Yes.
So is it true for dagger also?
I didn't check in the case of dagger, but that is generalized inverse, right? Dagger. Yeah. So maybe it is possible. I saw some result in that way. I got some papers evaluation. So I see it is long back, but I don't know whether it is available.
So we feel that if adjoint is replaced by dagger, some of the results can be done.
Yeah, but I think it's not easy. If you deal with this adjoint,
yes.
Another one is inverse. But we cannot expect the other classes have inverse. So we have if T is hypernormal, then T inverse is also hypernormal. But the other class we can't tell that the inverse is also belongs to the same class of orthonormal. For example, in our case, that if T is TWASP operator, then T inverse is TWTS operator. Yeah.
Another one is the joint spectrum of T. So do you have any example which is non-diagonal, which is non-empty?
Joint
points.
Yeah, it is a partition of spectrum. Yeah, it is possible to find out, but yeah, it is we can, because this is completely inside joint point spectrum is completely inside the point spectrum. Okay. Diagonals, I think, because all are the elements of sigma p. But if we can consider that by using maybe some shift operator, taking that shift operator.
Any other questions?
Invariant space.
Yes.
So, is there any further information provided the other invariant space?
Existence only we can even in the case of normal the spectral theorem gives invariant space. But it says the existence, but we can tell these are the candidates.
Supposing that you have more information did you additional information on the operators?
Yes, definitely. Because if you have invariant subspaces, then we have the restriction type of operator, and that is very useful in applied mathematics.
Any questions more? Okay, thank you, Dr. Prasad, for a wonderful talk.
Yeah, he's online. Oh yeah, somebody took Ramanand sir has.
Hello, Jagan Mohan. Are you available online?
Yeah, Professor Hari, I'm available.
He's available, but his.
Hello, Jagan Mohan.
Yeah.
Please unmute it.
Yes.
Hello, Jagan Mohan. Can you hear me?
Yeah, hi. Yeah, I hear you. Yeah. Hello?
Yeah.
Am I audible?
Speaker. Oh, he is muted. Which is the speaker, sir?
No, you're the.
Yes, one more.
He is muted still. You have to ask him to.
Yeah.
Am I audible now?
No, he is unmuted.
Good afternoon, sir.
No, this should not be muted. He's talking to him.
Good afternoon, sir. Jagan Mohan, sir.
Yeah, am I audible now?
No, sir, you are not audible.
Let me check once then.
Here it's audible. Sir, here it's audible, it seems. But
my-
I think speaker you have to change. Speaker.
Just a moment.
We are checking from our side, sir.
Yeah.
No, it's.
Sir, can you speak now?
Hello?
Yeah,
Yeah.
you are audible, sir.
Yeah, thanks.
So, let me introduce Dr. Jagan Mohan for the audience. I'm Dr. Ramananda introducing Jagan Mohan. Dr. Jannalagadda Jagan Mohan is currently Associate Professor in BITS, Pilani, Hyderabad. His research interests include
Spotlight.
differential equations, difference equations, fractional differential equations, fractional difference equations, and nonlinear analysis. He has presented several papers at national and international conferences. He was an assistant professor of mathematics at Maharaja's Postgraduate College,
I'll add.
Vijayanagaram, assistant professor of mathematics in Vigyan Institute of Information Technology, Visakhapatnam, assistant professor at MIT Manipal, and assistant professor senior at VIT Vellore.
That won't.
He has published more than 50 articles in several prestigious journals. Sir, over to you.
Good morning to all. Thank you, Dr. Ramananda, for your introduction. So I thank the organizers for allowing me to present a talk in this conference. So I'm going to share my slides. So is the screen audible to you all? Sorry, visible to you all? Yeah.
Yes, sir.
Is the screen visible? Yeah.
Yeah.
Is it visible?
Yes.
Yes, sir.
Yeah.
Yes, sir, it is.
Yeah. So thank you, Anand, once again. So the title of today's talk is Initial Value Problems of Nabla Fractional Calculus. So in this talk, so I'm going to introduce the concepts of Nabla fractional calculus. So we'll discuss some preliminaries or maybe the required results, basic results of Nabla fractional calculus. Then we'll move to the concept of linear Nabla fractional difference equations and how to find the solutions. Finally, we conclude with this talk with the comparison with integer order difference equations and fractional order difference equations. So let us move to the introductory concepts. So most of us, we know about fractional calculus. So fractional calculus is nothing but the theory of integrals and derivatives of arbitrary order. So arbitrary order, but mostly will take a real order. So it is nothing but the generalization of integer order differentiation and integer order integration. So we admit always that there are some drawbacks of this fractional derivatives and integrals, like the physical and geometrical representations. It's very difficult when we compare with integer order derivatives and integrals. But at the same time, fractional derivatives possess a non-local effect which compared to integer order derivatives. The reason behind is that we define fractional derivative through integral, not directly. So that's why fractional derivatives always admits non-local properties compared to their integer order counterparts. So that's why in those fields where non-locality plays a very important role, of course, fractional derivative gains advantage over integer order derivative. But I can't say like just replace an integer order derivative with a fractional derivative and just write a model. It's not like that. So the applications in which non-locality property plays a role, there obviously fractional derivative gains an advantage. So I'm not going through fractional calculus because the theme of this today's talk is the discretizations. So we have several monographs on fractional calculus, but I prefer to refer these two books by Kilbas et al. And Podlubny et al. Now I'll move towards the concepts of discrete fractional calculus. So just like fractional differential equations, so we'll have their discretized counterparts, fractional difference equations. So this concept is in the developing stage, and for the last 10 years, you'll find lots of, maybe I can say many research papers in this area about fractional difference equations. So at this point, I want to mention 3 important monographs in the last 10 years by Ferreri et al., Goodrich et al., and Ostalzik et al. So of which Goodrich is maybe the most popular one. Now, I'll come back to the same concept of non-locality here. Suppose if you take an integer order difference operator, and if you want to calculate the integer order difference at a particular point, you need the function's values only at 2 points. I'm just talking about a first order. But whereas if you take fractional order difference operator of order lying between 0 and 1, and if you want to calculate the value, you need more than 2 values of the function u. So that's why the fractional difference of any function contains information about all the earlier points, maybe starting from the starting point onwards. That's why it poses a long memory effect in compared to the integer order difference operator. So that's why I always again mention the same point that fractional difference equations also play a very important role in those places where non-locality plays an important role. For example, if you take a time series analysis, of course, non-locality plays a very important role. That's why you'll find lots of applications of fractional difference in time series analysis. So this is only one. Maybe we can discuss several applications which you can find in the book given by Ostalzik et al. So the author have given a wide variety of applications of fractional difference equations in this book. So though I'm not good at these applications, I mostly concentrate on the analysis. So I'll move ahead with the preliminaries. Now coming to the concept of a fractional difference, obviously we'll have 2 approaches in the literature. One is the forward difference approach, and the The second one is backward difference approach. So each approach has its own pros and cons, but I highlight an important point like in the forward difference approach, the arguments of U must contain real numbers, which is practically not feasible. So that's why most of us, we confine ourselves to NABLA approach. So in this talk, as I have already told, like I'll review the notations, definitions, and important results of NABLA fractional calculus. I'll analyze the solutions of initial value problems involving NABLA fractional difference equations. Finally, I'll compare in a couple of examples the advantage of fractional difference equations over integer order difference equations in NABLA perspective. Sorry. So before going to start with the preliminaries of the NABLA fractional calculus, I need some special functions, of which the first one is the gamma function, which we know already. So the gamma function is defined as gamma z equal to integral 0 to infinity t power z minus 1 e power minus t dt. So whenever real part of z is greater than 0, and of course this function can be extended to the other plane also, that we know already. Now I'll introduce three important concepts in discrete fractional calculus. So I'm adding a point here. Discrete fractional calculus means it is involving both forward and backward approaches. So the first domain is, I'm considering a domain NA. So the domain NA is defined as set of all discrete points A plus 1, A plus 2, and so on. A can be any real number. So I'll introduce two operators. One is forward jump operator and the other one is the backward jump operator. So the forward jump operator, the name itself says that it gives one jump forward, as well as the backward jump operator gives one jump backwards. So now we have two functions which we always come across in discrete cases. One is rising function and the other is falling function. So as you know, the rising function can be defined as follows in the slide which I have shown. T power n bar is, you have to multiply from t plus 1 up to t plus n minus 1. And of course, this product can be written in the form of gamma functions also, which motivates us to define the generalized rising function. So if you look at the definition of generalized rising function, we replace the n, the natural number, with a real number mu. But at the same time, if you replace, you look at the ratio gamma t plus mu by gamma t. So there will be an issue with gamma function if there are negative integers are 0. So accordingly, we have to define this. Similarly, we have another function called falling function, which also we come across in discrete calculus. And in the same lines, one can define the generalized falling function t mu under bar, that is gamma t plus 1 by gamma t minus mu plus 1. So these are the two prominent functions in discrete calculus, and we generalized them so that we can use them in discrete fractional calculus. So if you look at this graph, so when I'm taking alpha as 1, then t power alpha is just simply t power 1, which we come across in continuous case. T power alpha bar, which is a rising factorial, and t power alpha under bar is falling factorial. So all three will coincide. But when we take alpha as 0.98, a real number like this 0.98 between 0 and 1, then obviously there will be a small change. Maybe I can say, if you are approximating a continuous function with a discrete function, like you are approximating the continuous function t power alpha with its a rising factorial or by a falling factorial, there must be some error. So by these graphs, you can observe that. So if you increase alpha, obviously the error may be a little higher. So what I can say that maybe you can approximate this continuous function t bar alpha with its discrete counterparts. So I want to mention here is like t bar alpha, if you take in continuous case, their discrete counterparts are t bar alpha bar, that is a rising factorial, and t bar alpha bar, that is the falling factorial. So before going to proceed further for the definitions of difference operator and sum operator, we have one more important definition called the Taylor monomial. So Taylor monomial is just simply a byproduct of rising factorial or falling factorial, but still will make it more convenient to write in this notation. So the first definition is Nabla-Taylor monomial. So whenever n is a whole number, I'm defining the nth order Nabla-Taylor monomial as when we take n is 0, the function always becomes 1. And for n is a natural number, it is defined as t minus a bar n bar by n factor. If you carefully look at this Hn of Ta, it is simply a binomial coefficient only, but we are calling it as a Nabla-Taylor monomial. Both are same. If you expand t minus a power n bar using the gamma function or factorial function, you will come to a binomial coefficient only. Now we generalize the concept of this Taylor monomial to a fractional order just by replacing the natural number n with a real number mu. So h mu of Ta, which play an important role in the next slides, is t minus a bar mu bar by gamma mu plus 1. Maybe I can call it as a generalized binomial coefficient. Yeah. Now coming back to the first definition in operators, the first one is, which we know already, the backward difference operator or the Nabla difference operator. So if I take, I want to add a point here. So when we are trying to define the difference operators or sum operators, the domain of the function play a very important role, which I will discuss in the coming slides. So when U is a mapping from NA to R, and n is a natural number, the first order Nabla difference of U is defined as Nabla U of T is U of T minus U of T minus. So if you look at U, it is defined on NA. Obviously, Nabla U also is defined on NA plus 1. One jump forward here. And we can define the nth order Nabla difference operator in a recursive way also, right? So now look at the first definition, the Nabla difference of U, first order difference. So if I want to calculate Nabla U of T, I need only the values of U of T and U of T minus 1, only 2. So I'll discuss the same point in the coming slides. So now we look at the definition of Nabla sum. I can say it is the anti-difference. So whenever U is a mapping from NA plus 1 to R, so I can define the Nabla sum or the anti-difference, that is Nabla A par minus 1 U of T, which I'm writing in terms of integration for time being, which is nothing but summation starts from A plus 1 to T US. So I'm assuming that at A, this Nabla sum becomes 0. Now I want to repeat this first order sum into n sums by using the Cauchy's rule. So this rule we know in integration. This is Cauchy's formula for repeated integration. So the same formula can be applied to a repeated sum. So if you go to the second equation, I am repeating the same sum capital N number of times. So I can say that this is a n-fold sum. So finally, the left-hand side is an n-fold sum and the right-hand side is simply a single sum, but where the summand is different here. So in the first equation, I am interchanging n-fold integral into a single integral. Similarly, I can convert a n-fold summation into a single summation where there is a change in the summand. So with the help of this, now I am able to define the n-fold sum in a single summation way. So whenever U is a mapping from NA plus 1 to R and T is belonging to NA and capital N is a natural number, the nth order Nabla sum of U, which is based at A, is given as this equation. So left hand side, I am denoting that it is par minus n means the n-fold or the nth order sum, which is based at the point A, which is always given by a summation. Whenever it is based at A, summation starts from A plus 1 to T. The summand is a Nabla-Taylor monomial in 2 US. So I'll go back again to one more important point here. So if you look at the definition of first order sum or the nth order sum, it requires all the values of your U function from A plus 1 to T. So I can say that the sum operator is always non-local, which is true. Similarly, if you want to calculate the nth order sum also, it also requires the values of U from A plus 1 to T. So sum operator is always non-local. Now what I am doing is that I am generalizing the concept of natural number or integer order sum to a fractional order sum by replacing capital N by nu. So this slide shows that it is the nu order, that is nu is a real number. The nu order Nabla fractional sum of U is given by this definition. So if you look at the left hand side, so the summations index is A, means summation starts from A plus 1. Par minus nu means it is the sum of order nu of a given function U, which is given by summation S runs from A plus 1 to T, a Nabla fractional Taylor monomial weight in 2 US. So obviously, sum operator here is also non-local. Now, with these things in our mind, now we are able to define the difference operator through sum operator. Not like the integer order case, we are defining difference operator through sum. So whenever nu is a real number which is lying between two consecutive integers, n minus 1 and n, I can define the nth order sum as, so I'll write Nabla for n outside and n minus nth order sum inside. So I'm defining Nabla for n of n minus nth order sum. So if you look at the powers, if you add them, you will end up with nu only. So this type of approach is called Riemann-Lewis approach. And there is an interesting theorem that, so there is a simplified formula of Riemann-Lewis difference. So the nth order Riemann-Lewis difference is given by this formula. Just look at the definition. So again, if you want to calculate the difference operator, nth order difference of any given function, it requires the use values from A plus 1 to T. In integer order case, it is requiring only 2 values, whereas in this case, in this difference operator, it requires values from A plus 1 to T. So it is requiring a long memory effect for this. So similarly, we have another approach called Caputo type approach. So what is the difference between Caputo and Riemann-Lewis is that, so in Riemann-Lewis, we have taken the difference operator outside and sum operator inside. But here I'm taking sum operator outside and difference operator inside. As you know that they are not commutative, obviously these two differences are not the same. Of course, there is a relation between these two differences, but clearly it says that these two are two different approaches for Riemann-Liouville and Capito. Why you need two or why you need more approaches? Just look at the simple observation. If you take any constant and calculate the Capito difference, it always becomes zero. Why? Because there is a difference operator inside, so that's why it always becomes zero. Whereas if you take a Riemann-Liouville, inside is a sum operator, so you will not get Riemann-Liouville difference of a constant is zero. So that's why Capito difference has more applications than Riemann-Liouville because of these. It is having the properties in line with integer order difference. So you can discuss many other properties like power rule, which I am showing you in this slide. So again, composition rules. So same rules which we follow in integer order, it will work here. So you take the first property. So the first one is a sum operator. The second one is a sum operator. Obviously, you can add the powers like nabla a power minus mu. Nabla a power minus mu is nabla a power minus mu plus. So like that, you can define several properties of Riemann-Liouville and nabla in like this. So I'm skipping few properties because few properties are again more confusing here. Now I'll concentrate more on the coming topic, which is nabla fractional difference equation. Just like integer order difference equation, suppose if I take a nth order Riemann-Liouville fractional difference equal to 0, obviously nu is lying between n minus 1 and n. So as usual, it should have n linearly independent solutions. So those linearly independent solutions are simply the nabla fractional Taylor monomials. The same concept works for Capito equation also. This is also a Capito's homogeneous equation, and nu is also belongs to or lying between n minus 1 and n. It will have n linearly independent solutions. You look at these n linearly independent solutions in Capito case, they are simply integer order Taylor monomials. Whereas in Riemann-Liouville case, they are fractional order monomials. So that's why Capito is in line with integer order most of the time. So these two slides show the variation of constants which we study for differential and difference equations. So if you take a right hand side, a non-homogeneous term, you can apply a variation of constant formula to calculate the general solution. So this equation is for Riemann-Liouville and the next equation is for Capito. So likewise, you can calculate the general solutions in this way. Now I'll go to the last important topic with which I'll close this presentation, that is the exponential function. Suppose if you look at the equation, I'm taking a first order nabla difference equation. Nabla u of t is lambda ut and t is in na plus 1. I'm taking 1 as the initial condition. So this function is always known as the exponential function in integer order case, discrete. So the same concept can be generalized, and the new function we call as Mittag-Leffler function in the discrete fractional calculus. So it is defined by this equation E lambda alpha beta of Ta is given by this power series in lambda. Please remember lambda lies between -1 and 1 for the convergence condition. And also if you put alpha is 1 and beta is 0, you are getting the exponential function of nabla case. So that's why this Mittag-Leffler function can be treated as a exponential function for Nabla fractional case. So these are the graphs for positive lambda. They are always increasing. And these are all the graphs for lambda less than 0. They are all decreasing, as you know that. So same concepts can be repeated for eigenvalue problems. So if I'm taking an eigenvalue problem in Riemann-Liouville case, then we have n linearly independent eigenvectors. They are nothing but the Mittag-Leffler function. Similarly, if you take, there is a typo, I admit, there is a lambda ut here. Maybe in a hurry I have written. Same for a eigenvalue problem in Caputo case, you will have n linearly independent eigenfunctions. There is a lambda ut here. Maybe in a hurry I forgot. Sorry for that. Same can be applied for variation of constants in this case also. So it took a non-homogeneous term for the eigenvalue problem in Riemann-Liouville case. Similarly, a non-homogeneous term in the Caputo case. Yeah. So I'll conclude this presentation with a couple of applications, or maybe I can say an advantages. So many times I'm using the same word, the memory property. So integer order difference operators are having less memory compared to the fractional order difference operators. Fractional order difference operators have a long memory. That's why they are non-local in nature. And this non-locality has lots of applications. I'm giving you two simple examples which shows that the order of the fractional difference operator play an important role in the qualitative behavior of solutions. So look at these two equations. So the first equation is a Nabla difference equation, integer order is 1. The second equation is again a Nabla fractional difference equation, the order is nu. So for the first question, you know the solution, every solution is of this form. But this solution always goes to infinity as t tends to infinity because this Nabla fractional Taylor monomial goes to infinity as t tends to infinity. But if you try to calculate the solution of second equation, so it is given by equation 4. So one of the important properties of Nabla fractional Taylor monomial is if the index mu minus 1 and the index mu plus mu minus 1 goes like they are between -1 and 0, Nabla fractional Taylor monomials goes to 0 as t tends to infinity. So if you assume your mu plus mu is lying between 0 and 1, every solution of this Nabla fractional difference equation goes to 0 as t tends to infinity. So which is not possible in integer order case. Similarly, if you take equation 5 in integer order case, a similar equation of fractional case in 6. So every solution of equation 5 is a constant. If constant is not 0, every solution doesn't tends to 0 as t tends to infinity. But whereas if you take the equation number 6, which is the Riemann-Liouville type Nabla fractional difference equation, every solution is of the form 8. Using the same property of Nabla fractional Taylor monomial, every solution goes to 0 as t tends to infinity. So these two examples shows that the order of the fractional difference operator obviously plays an important role in describing the qualitative behavior of those systems. So with which I'm concluding my presentation. Thank you. Sir, your audio is in mute.
Sir, that was very informative talk on fractional difference operator and fractional difference equations. Audience, those who have questions, please come over the desk and ask your question. If there are no questions, I once again thank the Jagmohan sir. Thank you.
Thank you all for giving me an opportunity. Thank you.
Very nice, Jagan Mohan. Nice presentation. Thank you.
Thank you, sir. How are you, sir?
Yeah, fine, fine. How are you? Okay.
Yeah, I'm fine, sir. Hope other faculty are also fine.
Yes, yes, yes.
Yeah.
Happy New Year wishes. Late wishes.
Wish you the same, sir. Thank you.
Yeah. Yeah. Now we'll join for lunch. After that, two more talks.
Lunch is
Both
ready.
are online talks.
Lunch is ready.
Huh?
Lunch is ready.
Ready, yeah. Lunch is ready. Please join for lunch.
Three are there.
Three are there. One is a
One
video.
is video. Three talks are there.
Yeah, three talks.
Can I mute that?
Good afternoon, everyone. We have arrived third day of the event. In today's afternoon's first speaker, Professor Karin Teresa Howell from the University of Stellenbosch, South Africa. Good afternoon, madam. Hope you are online. Are you able to hear my voice?
Good afternoon. Yes, I can hear you. Thank you.
Good afternoon. Nice to meet you. Bye.
Likewise.
A very happy new year, madam.
Happy New Year to all of you as well.
So we'll start the talk in 2 minutes.
Could you confirm that you can see my slides?
Not yet.
Maybe a minute.
One. Yeah. Please share the screen.
On my side, it says on screen. Do you see my?
She has already started sharing the screen. But
Yeah,
it
but
is
good
not
afternoon,
visible.
Professor Teresa.
Drop message to me.
Can you see that?
Not yet.
Video is streaming smoothly, right? Right. I know it should or is the video also frozen?
Okay.
Video is also frozen.
Before starting, let me introduce Professor Katie Howell for that screen sharing. Dr. Karin Teresa Howell is presently working as Associate Professor in the Department of Mathematics, University of Stellenbosch, South Africa. Her research interest is mainly on near vector spaces, 19 publications, debated journals. She is a member of AMS South Africa executive team, associate faculty of AMS South Africa, advisory committee for mathematics of the South Africa Mathematical Forum, mathematics committee of NGA. Professor Karin held the position of being secretary of SAMF. She has received a Dean's Medal for the best BSc student and BSc honors student in the Faculty of Natural and Agricultural Sciences by University of the Free State in the year 2002 and 2003 respectively. She has also received many Vice Rectors Awards at Stellenbosch University for the excellence in teaching. So with this brief introduction, I welcome Professor Karin T. Howell to start presentation. Please share the screen, madam.
She has to join again. Some network issues. Network.
I have joined.
Yeah.
Could you
Now
just?
Yes, your screen is visible now.
Is that visible?
Yes, visible now.
Okay, thank you very much. So good afternoon, everyone. I apologize for the disruption. Somehow I got disconnected and then had to rejoin, but I think everything's working now. So I'd like to start by just thanking the organizers for inviting me to this conference. I would have liked to be in India, but unfortunately I can't join in person this time around, but I hope at some point to have the opportunity to visit. So my talk this afternoon is entitled The Weird and Wonderful World of Near Vector Spaces. So I'm going to divide it up into two parts. The first part will be based on some of the weird properties that we've discovered in the last few years. And then the wonderful will be part of some of the investigations that I'm involved in at present and some ideas for future work that I'd like to share. So my talk will consist of a short introduction. I'm going to introduce you to near vector spaces as first defined by Johannes Andre. Then I'm going to talk about some important concepts like regularity, spanning sets and subspaces. Some of the weirdness that I refer to is related to the fact that they have generators. And then I will delve into a discussion of some of the recent work and end off with some useful reading in case you are interested. So firstly, we're going to start with the definition of a near field, since we are going to look at two constructions of near vector spaces, first using copies of a near field, and I'm also going to speak briefly about copies, constructing using copies of a field. So fields are usually very well known and part of any first abstract algebra course. So what is a near field? Well, we're going to focus on right near fields, like you have the option of focusing on right or left nearings. So right near field is a set F together with two binary operations, such that we have an additive group under addition, and the non-zero elements of F under multiplication form a group. And then in this case, since it's a right near field, we have the right distributive law holding. Now, if F is a near field, then we can define what is called the kernel of F, and that's the set of all distributive elements of F. So in our case, what FD will be, the kernel, it will be all the elements that distribute from the left if we are working with a right near field. Now, if F is a near field, it is well known that the distributive elements form a subfield of it, and moreover, F is a vector space over Fd. And if we just look at the definition, it's not difficult to reason that every field is indeed a near field, as every ring is a near ring. Okay, so those are some definitions that we will need. Here is the smallest example of a finite near field. It's a finite Dixon near field, which we construct using the field of 9 elements. And what we do is we leave the addition as is, and we perturb the multiplication in the following way, depending on whether y is a square or not. And by doing this, we obtain an example of a right near field. And it's not difficult to check that this is not a field, since we will not have the left distributive law holding in general. And if we just investigate a little bit, it's not difficult to find the distributive elements of this finite Dixon near field, which are just the elements 0, 1, and 2, so the elements of Z3. So now I'd like to introduce you to the concept of a near vector space, which has been my area of specialization the last few years. So firstly, I just want to mention that there's more than one notion of a near vector space. Badelman had a definition of a near vector space where you use near ring modules, and Kozel also used a loop to define a different notion of a near vector space. This is the definition as penned by Andre. And this is where most of my work has been, looking at this definition and what we can do with these near vector spaces. Just a historical note, Andre's definition of his near vector space is based on his interest in geometry. So there's a very nice paper where he introduces them for the first time. It's not entitled Near Vector Spaces. It's a paper on incidence geometry that I can share if anyone is interested. And in there, he becomes interested in spaces where the join, so geometric spaces where the join is not commutative. And that leads into the concept of a near field space, and a near vector space then is an example of a near field space. So this definition is motivated by the geometry that he was interested in. So we call a pair a near vector space if we have an additive group V and a set of endomorphisms of V, which we will call A. And there are some requirements for A. It must contain the endomorphism 0, the identity, and minus the identity. And A star, so all the non-zero elements of A should form a subgroup of the group of automorphisms of V. And then just as with vector spaces, we would like A to act fixed point free on V, which means if we have that X alpha is equal to X beta, then either X must be 0 or alpha must be equal to beta. You'll notice here that we write the scalars on the right. This is in keeping with how Andre did it. So we used to, with vector spaces, writing the scalars on the left, but since we'll be making use of right near fields in our constructions, the multiplication will be written on the right. We also have something that sets the structure apart from a vector space and becomes very important in the study of near vector spaces. And that's a subset of V that consists of all the vectors that have this property here. So what we have is that for any scalars alpha and beta, we can find a gamma such that X alpha plus X beta is X gamma. So the quasi-kernel collects together all the elements that have this linear property. So we refer to V as the near vector space over A. The elements of V are called vectors and the members of A are called scalars. So we're mimicking what we do for vector space theory here. And the action of A on V is called scalar multiplication. You may wonder, as if we were looking at vector spaces, whether V under addition will be an abelian group. And the fact that minus the identity is an A ensures that it is. And then we want to talk about basis and dimension. So what would the dimension of a near vector space be? Well, it will be uniquely determined by the cardinality of an independent generating set. So independence is defined in the same way as with vector spaces. In fact, technically, Andre defines independence first in terms of a dependence relation, but later proves that it exactly coincides with the notion of independence that we have for vector spaces. But notice here that the generating set will be a subset of the quasi-kernel. So what happens with near vector spaces is the quasi-kernel encodes the linear part of the near vector space, so the part that behaves as if as a vector space most closely, and that is how we will define a basis. We will look at a generating independent set that is a subset of the quasi-kernel. And then it's not difficult, if we just look at the axioms and what is required, to notice that every vector space is a near vector space where the quasi-kernel is the whole space, which is what we'd want when we look at near structures. We have that every ring is a near ring. We have that every near field is a field, and so forth. Right, so as a very accessible first example, and here just to make it accessible, oh, I see I'm missing a Y there, but I just put the scalar multiplication on the left, whereas in the rest of the slides I'll have it on the right, but just to give you a feel for it. So I apologize, there's a Y missing here. If we just take 2 copies of Z5 and we define the scalar multiplication as follows. So what you'll see is when we multiply by a scalar alpha here we multiply in the normal way, and in the second component, we multiply by alpha to the 3. So what's missing here is alpha to the 3y. And this is the smallest example of a proper near vector space constructed from a finite field. And in a moment, I'll explain to you about regularity and what its quasi-kernel is, but this is also an example of a non-regular near vector space. So I will go into the detail of that in a moment. So one of the most important results in near vector space theory was by Van der Walt, who was originally from Stellenbosch University. And he proved this theorem, which I refer to as the construction theorem for near vector spaces. And it gives us a recipe for constructing near vector spaces in general. So just to go back, we're going to understand now how I knew that this would give rise to a near vector space, and it's an application of this theorem. So without reading through the theorem and going into all the detail, what we're going to do is we're going to start either with a field or with a near field. We're going to take a certain number of copies of it. So we're going to take, say, n copies of F, whether it's a field or near field. Then we're going to find some semi-group isomorphisms, and our A is going to be the same F that we chose to duplicate. So we're going to put the same F as our set of endomorphisms. So just as with vector spaces, we take copies of a field over itself. We're going to do the same thing here, copies of a near field over itself, which would mean that this F would then be the near field, or if we started off with a field, this A would then be F. So we need some multiplicative group isomorphisms, and group theory gives us access to those, whether we're working with a field or a near field. And then you can see, if I just simply jump to the bottom here, how we define the scalar multiplication is then the component times that multiplicative automorphism acting on the scalar, which is what happened here. The multiplicative automorphism here that was used is cubing. And so we took the scalar, we cubed it and multiplied by y. So this gives us a very neat way of constructing all near vector spaces. But to get to the weirdness that I'd like to share with you, we're going to focus on a particular one at present, which is where we take n copies of a near field F. And we're going to take the identity automorphism. So very simply, we're just going to take every component and multiply it by alpha. And that's already enough to get some very weird behavior that I want to share with you. So basically, we're going to take in every component the semi-group automorphism to be the identity. Now, this type of construction gives us a near vector space. It's not a vector space, it's a near vector space, but it has the property that it is closest to traditional vector spaces in terms of its behavior and properties and theorems that we can prove. And just for ease of use, we will denote an instance of such a near vector space where we take all the scalars and we just multiply by them to be denoted by VF. Right, so we're going to come back to that construction so that I can point out some of the weirdness that I'd like to share with you. But first, I want to talk about regularity. So regularity is central to Andre's near vector space theory. So let me first explain to you what it is. A near vector space is said to be regular if any two non-zero vectors of the quasi-kernel, so remember the quasi-kernel is all the linear elements that we've collected together, and they're either the set V or they're a subset of V. Now, if any two vectors of the quasi-kernel have the property that we can find a non-zero scalar, remember the scalars are endomorphisms, such that the sum U plus lambda V is back in the quasi-kernel, then we have a regular near vector space. And if we just think about it for a moment, this property does hold in general for vector spaces. So this is something special for near vector spaces. And if we can do this for any two vectors belonging to the quasi-kernel that are non-zero, then the space is said to be regular. Now, why is regularity important? Because of the next theorem that Andre proved, which is the decomposition theorem. And what he showed is that any near vector space can be decomposed into the direct sum of regular maximal subspaces, which means you can take any near vector space and decompose it. And I was listening to Professor Pulse's talk about decomposition, and this is where decomposition is very important in near vector space theory, because it gives us access to the regular parts, and the regular parts are the parts that most behave like traditional vector spaces. So normally in the study of near vector spaces in any of the branches of mathematics that I'm going to be talking about a bit later, the strategy is always to first study the regular parts or regular subspaces or regular near vector spaces, and then go over into the non-regular. And we are always able to study them by the decomposition theorem, since we know that any near vector space will decompose into regular parts. So this decomposition is also unique, and it's called the canonical decomposition of the near vector space. So in Andre's original paper on near vector spaces, he describes these regular subspaces or regular near vector spaces as the building blocks of the theory, which is exactly clear to us now if we look at the decomposition theorem. Now, you may wonder if it's always true that if V is regular, the quasi-kernel must be the whole space. Well, certainly we can see for vector spaces, we always have regularity. And in that situation, V is the quasi-kernel, since all our elements have this nice linearity that we capture in the quasi-kernel. But the converse is not true in general, which means that we have near vector spaces that are regular, where the quasi-kernel is not the entire space. Right, we have some very nice examples of regular near vector spaces and also properties of them. So the first is the lemma that Andre proved, and that near field construction that I spoke of earlier on my slides, where we took copies of a near field over itself and we used the identity in every component. That is an example then of a regular near vector space. And what's interesting about that one, which I gave an instance of here at the bottom, is it's exactly an example of something that's regular, but the quasi-kernel is not the entire space. In fact, the quasi-kernel will be the union of these two sets, where these DI come from the distributive elements, and we can certainly find elements that do not belong to the quasi-kernel, but do belong to V. Right, so just with vector spaces, we want the concept of a subspace. So a subspace is defined in this way. And the reason I defined it in this way, Andre did not originally define what his notion of a subspace is, although it was clear that he thought of it in the normal context of vector spaces. But in line with the fact that the quasi-kernel must generate the whole space, this is the definition that I penned in a paper I wrote in 2015. So what we require is that any subspace be generated by a subset of the generating set of the space to which it belongs. And this then gives us access to the notion of subspaces. You may wonder if we have the normal property like for vector spaces, that if we have a subset that's closed under addition and scalar multiplication, will it be a subspace? And in this paper in 2015, I thought it was pretty obvious that that is the case, and I proved it. But then subsequently, a colleague of mine in 2019 picked up that there was a gap in that proof, and it was subsequently fixed in a paper that we published and that appeared last year. And I also then subsequently had a student who proved the subspace test using geometric techniques. So in general, now we can say that a subspace is a subset that's closed under addition and scalar multiplication, which is what I think Andre always intended. Right, so this is getting to the weird bits that I want to share with you. So we can define the span of a near vector space, and I chose to define it as the intersection of all subspaces that contain S. And this is then a subspace of the near vector space. And there are some nice properties we can prove regarding span. One of the interesting properties is that the span of a single vector is one-dimensional, if and only if that vector belongs to the quasi-kernel. And something that we're not used to is if you take any element that lies inside V outside the quasi-kernel, the span does not need to be one-dimensional, which already is quite different from what we know of vector spaces. Even stranger is the following question, which is work that I completed with a student, Sorgu Sanon, who went on to complete his PhD in Germany. So we asked if it is possible, which seems even just strange to ask, but could we have that for these near vector spaces, that there is a vector such that the span of V is the whole near vector space, which of course is not the case for vectors and for vector spaces. And so we defined the notion of a generator. So a vector is a generator if it has exactly that property. And we were able to prove some results around when we think a near vector space will have a generator. And in order to do that, we defined the notion of the dimension of a vector. So I'm not going to spend too much time on that, but I just want to show you some of the results. So in the beginning, we were convinced that you had to look at proper near field constructions. So the one I spoke of earlier, where we took copies of a near field, in this case, copies of a proper near field. So the easiest one to use here is a Dixon near field. And if you have this property where the components of the vector have the property that if you sum scalar multiples of distributive elements and they vanish, and you are able to show that that means all the distributive elements must be 0, then this vector will be a generator, which is not an easy way to look for a generator, but this is one characterization. Another result that Sorgu was able to prove was that depending on the order of F, if it has this property that the order of F is the same as the order of the distributive elements of F raised to M, then this would also be a generator. So that gave us another result linking us to generators. So here's the first example that we became aware of having this very strange property that we can find an element in the near vector space outside the quasi-kernel that is able to generate the entire space, which is very weird. So for example, 1 gamma here, where gamma is the root of the polynomial you use to construct the underlying finite field, that would be a generator of this two-dimensional near vector space. So in the last year or two, I have also engaged in a project with Professor Nancy Newdower from Pacific State University, and we asked if this is only the case for finite near fields, so finite proper near fields. And we were starting to wonder whether it's the case for finite fields as well. So namely, if we constructed a near vector space from copies of fields, is it also possible to find generators? And in fact, it is, which was quite surprising since this would have been easier to look at first, but we went backwards. But we were able to show that if you take copies of a finite field and you construct a near vector space using von der Waals theorem, and just to say there are papers to explain how to find all the multiplicative automorphisms of the field and how to go about constructing those near vector spaces, then simply any element that sits outside the quasi-kernel will have the property, well, I must just put some restrictions on that, any element with non-zero components, so all the elements must be non-zero, all the components making up the element must be non-zero, then that will be a generator of the entire near vector space. So here's another example. And here I just put the scalars on the left since the first time I gave it, I put it on the left as well. So this is the first example I gave you of a near vector space. So you can see the scalar multiplication here is normal multiplication. And again, sorry, I copied and pasted, the y is missing here. But this is a near vector space. It's non-regular. And the quasi-kernel looks like this. And basically any element, so here again, if we just took 1, 1 or 1, 2 or any element that is not in the quasi-kernel, it will have the property that we are able to generate the entire space. Now you may wonder, what does this mean in terms of having a basis? Remember, Andre defined a basis to be an independent generating set that sits inside the quasi-kernel. So despite having a generator, we would not say that the basis for this near vector space is the set containing the element 1, 1. We will still have that, according to Andre's definition, the basis must be a subset of the quasi-kernel. So the basis will be 1, 0, 0, 1, our traditional canonical basis, which is strange since we now have something smaller that generates sitting outside the quasi-kernel, but sticking to Andre's theorem, here we have a basis, 1, 0, 0, 1, inside the quasi-kernel, and outside the quasi-kernel, we have a generator 1, 1. So now I want to talk about the wonderful, that's the weird. So often when I talk about this work, one of the first questions is, great, it's interesting, but why? And the but why has been something that's been of interest to me since I started studying near vector spaces. I always think that they are underappreciated, and I think in the next few years, we are going to see the fruits of near vector spaces and where they are useful. And some of the work that I have been involved in that has started to unravel near vector spaces and what new examples and avenues of exploration they can open up has been re-looking at the geometry of Andre's work. So going back to the roots of the work and the first papers he wrote about the geometry. So he looked at incidence geometry. And if you read the paper and you see the motivation of his work, it gives rise to some very interesting geometric results. And I just recently had a student graduate with a PhD, and in his thesis, he was able to link the geometric structures that Andre used to define near vector spaces and bring them into the algebraic world. So we connected the geometry to the algebra, and he was able to prove some results through that route. Another avenue that I'm very interested in is looking at the matroids of near vector spaces. So matroids capture independence and dependence of structures. And that has been something that I've worked with Professor Neudauer. Matroid theory is also closely connected to geometry. So my hope is that not only will near vector spaces lead to some new geometric structures of interest, which I think they already have, but also give us some new matroid examples with properties that may be of interest in that branch of mathematics as well. And then recently I completed a paper with Professor Davaz and my student, Jacques Rabi, on hyper near vector spaces, where we looked at how we would define a near vector space for hyperstructures. So something that would have the same properties as Andre's near vector space, but in a hyper setting. So before I close and share the bibliography with you, I'd like to share with you my big dream for near vector spaces. So I mentioned the application part. So many systems in natural sciences, and not only natural sciences, specifically in engineering, I've had some very interesting conversations with people, but also in the finance industry. So many applications that are used and systems that are used to predict are based on the assumption that the systems that are being studied are linear, which we all know is in the majority of cases not true. Most things in science and in applications are very non-linear. And to date, there are not mathematical structures that can adequately capture the non-linearity of certain systems, even in nature or in finance or in engineering. So long term, I have a dream for near vector spaces becoming the structure that captures the non-linear behavior of many real world applications in science and in finance and even in computer science. There are many applications where there's a non-linearity, and the way most of it is dealt with at the moment is making the assumption that things are linear. And with that, we lose a lot of the information that actually depicts what's going on in the system. So that is my big dream for the work, that someone one day listening to this will take this further and actually go and try and find the applications. And that would be lovely to see. So that is my talk. Here is some reading if you're interested. I just want to share that if you are interested in reading up about near vector spaces, here is some very nice papers. This paper so it's the fourth paper by myself and a colleague, Sophie Marquez, towards an intuitive understanding of near vector spaces, is a very nice paper we recently wrote that has some very nice new results, but it also just gives an explanation of what we think was the algebra and the intuition behind how Andre defined his near vector spaces. And then the first paper is the original paper by Andre on near vector spaces. It's in German. But it is a lovely paper to have a look at. And there he also describes some of the geometry that influenced his work. So I'm just going to scroll through them so you can see some of the work. And if you're interested, you're welcome to contact me with any questions you may have. So thank you for your time.
Professor Howell, a wonderful talk. Now is the time for questions from audience. Any questions, please, either offline or online participants. Right.
Hello. Am I audible?
Yes.
Yes, yes.
Yeah, hello, Professor Havel. Myself, Om Prakash from IIT Patna, India.
Yes. Continue, please. Yeah, please, you can
So,
ask.
as you have seen in your conclusion that you have been studying geometrically about the near vector space. So, let me know, have you any simplified example of the geometrical object that has been forming the near vector space?
Yes, so if you share your details, I can send the paper to you. But so in a normal projective space, the join is commutative. So in the paper that Andre wrote, he gives it's almost like a near projective space. So it's the same as when you grow from rings to near rings. So you lose some of the linearity in a sense. And he gives a very nice example, and that was his motivation originally. So I can send that to you and you can have a look. And the example that he gives of this space that has less linearity is actually a near field space. And every near vector space is a near field space. So that's how he came about the idea of a near vector space.
Yeah, but I would like to visualize it geometrically. What example would be more suitable for this notion? Geometrical objects.
Yeah, so it's related to projective spaces. So if you're interested in projective spaces, you'll be interested in these spaces.
Okay.
Does that answer your question?
Yeah, as you told about the projective spaces, projective geometric spaces, one of example of near vector space, as I understand what you are trying to say.
Yes. So he defines a near affine space. So actually in the paper he starts with defining a near affine space, and then he adds some axioms to it, and then he gets to the notion of a near field space. So it's this notion of nearness, and he drops some of the traditional axioms of an affine space to get to a near affine space. And then he gets to by adding some axioms that he picks, he gets to what is called a near field space. And it's all based on the notion that the join is not commutative in general. And then he gives as a first example of a near field space, this construction where you take copies of a near field over itself with the identity multiplication. And that becomes his first example of a near field space. So the geometry doesn't have applications yet, but it's the first, I would say, the first attempt at trying to define the notion of a near affine space. So yeah, we're hoping to take it even further and come up.
In terms of notion. Of course, another notion you have been giving an example, but anyway, thanks a lot for your nice presentation.
Pleasure.
I think Professor is more mature in this regard. Yeah, anyway, go ahead.
Yeah. Any
Thank you.
Any questions from audience? Any questions, please? Online?
Hi, Professor Paul.
Yeah. I have a small question. Maybe it may be very simple. You have shown that span B equal to V, right? Somewhere in the question.
Yes. So we have some examples where that happens.
Yeah. Is there any relevance with the monogenic N group? Suppose if you have an element where it spans the entire group, right?
Sorry, could you just repeat the question? I didn't get that.
Yeah. For example, if your group is monogenic, N group, that has only one generator, right?
Yes.
N G equal to G entire group you are getting. Is there any relevance with this, your question?
No, so the examples that we have, in fact, there are many generators. Any element outside the quasi-kernel will do the job. So there's not a uniqueness. Any element outside the quasi-kernel will generate. With non-zero components, of course.
Okay. Yeah, thank you. If there are no questions, thank the speaker. very nice presentation and very nice illustrations.
Thank you.
I also request Professor K.T. Howell to chair the next session. Probably it's okay for you, right?
Yes, perfect.
Yes. Thank you. Switch over to the next presentation. Thank you.
Check in chat first. Participants.
Datta, are you able to hear us?
Yes, I can hear you.
Okay. Can I tell the chairing person to start the session?
Thank you. So it's my great pleasure this afternoon to welcome Professor Datta, Heman Datta. I hope I'm saying it correctly. He's a faculty member in the Department of Mathematics at Guwahati University, India. His current topics of research interest are in the areas of mathematical analysis and modeling. He has written over 170 research works, including journal articles, book chapters, and conference proceedings papers. He has also published several books, including reference books, edited volumes, and conference proceedings. He is on the editorial board of some Scopus Index journals and has organized many academic events and is associated with many events in different capacities. He has delivered several invited talks and served as a resource person at national and international level. He has also visited some foreign academic institutions on invitations. So welcome, Professor Datta, and I'm handing over to you. We look forward to your talk.
Thank you, Professor Pavel. Can you see my slides?
Yes.
Yes.
Okay, thank you. So the title of my talk is Stability and Applications of Cauchy and Rational Types of Functional Equations. So here is the outline of my talk. So first, a very brief introduction. Functional equations are equations in which the unknown are functions. The field of functional equation includes differential equations, difference equations and iterations, and integral equations. Solving a functional equation means finding all functions that satisfy the functional equations. To get a solution, functions must often be restricted to a specific type such as analytic, bounded, continuous, convex, differentiable, measurable, or monotonic. So the theory of functional equation has a very long history. So Nicolas Oresome defined uniformly deformed qualities in 1347 using some equation which amount to these functional equations in 3 variables, and this equation is known as the first functional equation in several variables. However, functional equations in a single variable in the form of recurrence sequences date back to antiquity, and we can say from Archimedes' time. So other earlier examples of functional equations can also be found in some works of Oresome in 1352, Napier in 1614, 1617, 1620, in Kepler's work published in 1624, Galileo 1638, Abel 1823, 1826, etc. And all these are very nicely presented in a book of Castillo. Later I will show this book. The majority of recent advances in functional equation theory have been published mainly in journals in mathematics. However, many books and book chapters are now available to interested readers to go through the historical development as well as recent development. So in this connection, I want to particularly mention about this book by this Hungarian mathematician János Ezzel. And this book was published in 1966. And this book deserves a special mention because many mathematicians were drawn to the field or attracted to the field of functional equation as a result of this book. So here are some preliminary notion about functional equation. There are many definitions of functional equation, but here we are going to follow the definition provided by J. Ezzel. So functional equation is an equation in which both sides are terms constructed from the finite number of unknown function and a finite number of independent variables. So each system of functional equation is a set of two or more functional equation. A solution of a functional equation is a function which satisfies the equation. A function or a set of function is said to be a particular solution of a functional equation or a system of functional equation if it satisfies the functional equation or a system of functional equation. The general solution of a functional equation or a system of functional equation is the totality of particular solutions. So let us begin with a very simple examples of functional equation. So let us try to find out all the function f which satisfies this functional relationship f of x plus y whole square is equal to f of x square plus f of y square, assuming that x and y are real numbers or f is a real valued function of real variable. So here by substituting x and y equal to 0, we get f0 square is equal to f0 square plus f of 0 square, and this implies that f of 0 is equal to 0. Again by substituting y is equal minus x in place of y, we arrive at this 0 is equal to f of x square plus f of minus x whole square. So from this, we can easily conclude that f of x square is equal to 0 for all x, and ultimately f of x is equal to 0 is the only solution. Sorry. Now we show some examples of Cauchy's functional equation. Of course, there are many generalizations in different directions of Cauchy's functional equations. So let us denote by R plus and R double plus the set of real number, the set of non-negative real numbers, and the set of positive real number respectively. So there are four basic types of Cauchy's functional equation. Type 1, f of x plus y is equal to f of x plus f of y, and x and y belongs to R. Type 2, f of x plus y is equal to fx into f of y, where xy belongs to R or R double plus. Type 3, f of xy is equal to f of x plus f of y, xy belongs to R double plus or R excluding the point 0. Type 4, f of xy is equal to f of x into f of y, xy belongs to I double plus or R excluding the point 0. And here f is a real valued function of real variable. And Cauchy solved this equation of type 1 way back in 1821, and the most general solution till known and given by Cauchy himself is this one. If Cauchy's equation of type 1 is satisfied for all real x and y, and if the function f is a continuous at a point, or b negative for small x, or c bounded in an interval, or d integrable or immeasurable, then f of x is equal to cx and x belongs to R, where c is an arbitrary constant for all real x. And this is the most general solution of Cauchy's equation of type 1. Sorry. And there are, as I told, there are many generalizations in various directions of Cauchy's functional equation. So Pexidar equation is one among them. So there are also four types of Pexidar's equations. Type 1, f of x plus y is equal to gx plus hy, where xy belongs to R or this closed interval with endpoints a and b. F of x plus y is equal to gx into hy, xy belongs to R. F of type 3, f of xy is equal to gx plus hy, where xy belongs to R or I double plus or R excluding the point 0. Type 4, f of xy is equal to g of x into h of y, xy belongs to I double plus or R excluding the point 0. And here f, g, and h are real functions of real variable. And the most general system of solution of Pexidar's equation of type 1 with f continuous at a point or non-negative for small x or bounded in an interval is this one. F of x is equal to cx plus a plus b, g of x is equal to cx plus a, and hx is equal to cx plus b. And here a, b, c are arbitrary constant. And Pexidar himself solved this in 1903. So let us check how Cauchy's functional equation can be of use in practical situation, and also we'll here try to some idea how the stability of functional question may arise. So this is a very simple example of computing simple interest. So here we'll see the role of functional Cauchy's functional equation, and here also we'll see how stability may arise. We assume that the formula of finding simple interest of a deposit of an amount P for a time duration T is unknown, but given by the function capital I, is a function of P and T. At the end of the duration T, a depositor must receive the same interest if he deposits the amount P plus Q in one account, or he deposits the amount P in one account and amount Q in another account. So this situation we can explain by this functional equation, Cauchy's additive equation. Again, at the end of the time duration T plus U, a depositor must receive the same interest if he deposits the amount P for the duration T plus U, or he deposits the amount P first for the duration T and later for the duration E. So we can write this situation in terms of this Cauchy's additive functional equation. Capital IP here T plus U time. This must be, the return must be equal to this capital IP of T plus capital IP of U. So the other problem reduces to finding solution of this system of two functional equations given by 1 and 2. And here P, A, Q, this is amount, T and U at time. So these are all belongs to non-negative real numbers. And the solution of the first equation is this one. Capital IP of T is equal to C of TP. And substituting this in the second equation, we get this after a simplification. We arrive at this C of T plus U is equal to CT plus C of U. This is again a Cauchy's additive functional equation, and we know the solution of this type of equation. This is equal to C of T is equal to KT. So ultimately we get I of PT is equal to KP of T. And here the constant K is the interest rate. And we all know this. This is a well-known formula of the simple interest. And let us see how the stability question may arise. If we deposit a larger amount for the same period of time, or we deposit same amount for a longer period of time, bank return higher interest rate. So the simple interest assumptions in 1 and 2 do not hold in reality. Or we can say this in this way: if a bank does not follow the below policies, that means if the bank is not returning higher interest on depositing bigger amount for the same period, and in the second case, keeping the same amount for a bigger period, if the bank is not returning the higher interest rate, that means it is inviting its customer to deposit their money in many accounts with a low amount in each account in the first case, and also inviting its customer to withdraw the money every day and deposit it again in a new account in the second case. So when the equality is replaced by inequality, the account instability may occur. So later on we'll see that when we'll define the stability of functional equation, there also we'll see that the stability questions of functional equation arises when the equality is replaced by inequality. This is just a simple example. So simple interest is the optimal way of keeping account stability by giving the least possible interest. So let us now go through some types of rational functional equation. Let us now consider another type of functional equations. G of m plus n is equal to G of m into G of n by G of m plus G of n. And this equation is called a rational functional equation because its solution is of this form, rational type. G of m is equal to k by m, where k is a constant, and easily you can say that this is a particular solution of this equation 4. Let us now check how this equation can be of physical relevance. So we know conductance is the opposite of resistance, and this is the measure of how easy it is for electric current to flow through something. And mathematically, we know conductance equals the reciprocal of resistance. And let us consider two resistors R1 and R2 with resistances 1 by X and 1 by Y respectively, and they are connected in parallel as shown in this figure. Then X and Y are the conductances of the resistors R1 and R2 respectively, and X plus Y is the total circuit conductance. The equivalent resistance of loads wide in parallel can be obtained by this mathematical formula. 1 by total circuit conduction is equal to total equivalent resistance of the parallel circuit. So from here we can say this 1 by total circuit reduction is X plus Y, and this is equal to 1 by X into 1 by Y by 1 by X plus 1 by Y. Since from this equation we can see that K by M is a solution. So by taking K is equal to 1, sorry. So by taking K is equal to 1, we can here we can K by M is a solution. So here taking K is equal to 1, we can say that this rational functional equation has relevance, physical relevance in this circuit. Next, we consider the system of two functional equations. R of x plus u y is equal to R of xy into R of uy, R of xy plus R of uy. And second one, R of x, y plus b is equal to R of xy into R of xb by R of xy plus R of xb. And it is easy to see that R of xy is equal to 1 by xy is the solution of the system of these functional equations given by 6. So in recently we studied, this is our own work. Recently we studied a new rational functional equation comprising of two variables, and we provided its solution, and also we have given some applications also. And later on I will show that we have studied the stability of this type of rational functional equations. So we have introduced these rational functional equations, and we have shown that if a function f satisfies the system of rational functional equations given in 6, then it also satisfies the rational functional equation that we introduced given by 7. So we can say that 1 by xy is also a particular solution of these functional equations. We have also shown its physical relevance. Let us apply a force F, capital F, tangential to the top surface of a block whose bottom AB is fixed, as shown in this figure. Under the action of this tangential force, the body suffers a slight change in shape, its volumes remaining unchanged. The side AD of the block is sheared through an angle small v to the position AD. So this is depicted in this figure. This one is the sheared angle V, and this is the tangential force. So the body is deformed into this position given by dots. The area of the top surface is, if the area of the top surface is U, then the shear stress is F, capital F by U. And shear modulus or modulus of rigidity of the material of the object is given by this formula. Rigidity modulus is equal to shear stress by shear strain. So this is equal to F by U, this one F by U, and shear strain is equal to P. So this is F by U of phi. So the formula 8 is used to find modulus of rigidity of any material. Let us denote the modulus of rigidity by the function R of U phi. Then R of Ui phi j be the modulus of rigidity of the material with shear angle phi j and with top surface area Ui. Now suppose if the area of the top surface is U1 plus U2 and the side AD of the block is sheared through an angle P1 plus P2 to the position AD dash, then the rigidity modulus can be calculated by taking 1/4 of the harmonic means of the moduli of rigidity, this R of U1 Phi1, R of U1 Phi2, R of U2 Phi1, and R of U2 Phi2, keeping the force F constant in all cases. Thus, our dysfunctional equation has relevance in establishing modulus of rigidity of several cases of the same material. Now let us check the stability analysis. So a certain formula or equation can be used to model a physical process if a small change in the formula or equation causes a small change in the corresponding result. When this happens, the formula or equation is said to be stable. The concept of stability for a functional equation emerges when the functional equation is replaced by an inequality that acts as a perturbation to the equation. A functional equation stability question is how the solution of the pertinent inequality differs from that of the given functional equation. A functional equation capital F is said to be stable if any function small f satisfy the equation approximately is near to exact solution of capital F. Moreover, a functional equation capital F is hyperstable if any function small f satisfying the equation approximately is a true solution of capital F. A question concerning stability of homomorphism between groups was posed by S.M. Ulam in 1940 in a conference in this form. Suppose capital G is a group, HD is a metric group, and F is a mapping from G to H for any epsilon, positive epsilon. Does there exist a delta depending on epsilon, positive delta, such that D of f of xy comma f of x into f of y is less than equal to delta wholes for all xy belongs to capital G and implies that there is a homomorphism capital M from G to H which is near to f by epsilon D of fx comma m of x less than equal to epsilon for all h belongs to C. So in other words, if a mapping is almost homomorphism, then is there a true homomorphism near it with small error as much as possible? If the answer is affirmative, we would call that the equation f of xy is equal to f of x into f of y of homomorphism is stable. And these kind of questions form the material of the stability theory for functional equations. S.M. Ulam's questions were affirmatively answered by D.H. Hayers in the next year, 1941, and next we present his original theorem. If f is a mapping from I to R, satisfying this condition, mod of f of x plus y minus f of x minus f of y, this quantity f of x plus y minus f of x minus f of y, this is called Cauchy difference. This is less than equal to delta. This means bounded Cauchy difference. For some positive delta and for all xy belongs to R, then there exists a unique additive function A from I to R such that this A is near to F by this delta. For that here the delta is the same. For all x belongs to R. The proof of this theorem also works for function f from E to F, where E and F are Banach spaces. And the actual additive function is this one, limit of n tends to infinity f small f up to the power nx by 2 to the power n. And this pioneer work of D.H. Hayes can be expressed as the Cauchy functional equation f of x plus y is equal to f of x plus f of y is stable for any pair of Banach spaces. And this function, this x of y to f of x plus y minus f of x minus f of y is called the Cauchy difference of the function f. So function with a bounded Cauchy difference is called approximately additive or delta additive if the Cauchy difference is bounded by the constant delta, like this case 9, given in 9. Any result similar to this theorem is known as highest Coulomb stability of the corresponding functional equation. It is possible to provide stability results similar to highest for function with unbounded Cauchy difference. Auki in 1950 was the first to prove such a result for an additive function. P.M. Gracias in 1978 then proved a similar result for linear mapping on Banach spaces. So below we present the Russia's results that inspired a lot of activity in the stability theory of functional equation. So this is the theorem, actual theorem, original one given by T.M. Russias. If f is a mapping from I to R, set real function satisfying this condition, mod of f of x plus y minus f of x minus f of y less than equal to delta mod of x to the power p plus mod of y to the power p for some positive delta and p is greater than equal to 0 and strictly less than 1 for all xy belongs to R, then there exists a unique additive function satisfying this condition, mod of fx minus capital Ax less than equal to twice delta by 2 minus 2 to the power p mod of x to the power p for all x belongs to R. So here if we put p is equal to n, then this theorem implies the previous one. And this theorem holds for all R excluding 1. So any result similar to this theorem, the last one, is known as the higher Coulomb-Racia stability of the corresponding functional equations. And works of Auki and Racias have been generalized by many mathematicians by weakening the conditions for the Cauchy differences. And moreover, generalization of the previous two theorems can also be initiated by considering this inequality by means of some control function. And we are also working in this direction by considering some control function like this, mod of f of x plus y minus f of y, x minus f of y less than equal to phi of xy, and here phi is a function from x cross x to R plus, and here x is a Banach space. So Borgin in 1951 was the first to consider the inequality 10 and stated without proof that if phi depends on mod of x and mod of y is monotonic, non-decreasing, and symmetric in mod of x and mod of y, and moreover, this series summation from k to infinity 1 by 2 to the power k phi up to the power kx comma to the power ky converges for each small x belongs to R. Then f of x minus a of x less than equal to a of x, where x is equal to 1 by 2 summation of k from 0 to infinity 1 by 2 to the power k phi up to the power kx comma to the power kx. 40 and Komenick in 1980 independently obtained this result. Suppose x plus is a commutative semigroup, not semi-ring, semigroup. If x plus is a commutative semigroup and E is a Banach space, if the function f from x to E and this control function phi from x to the 2 to the power R plus satisfy the inequality norm of f of x plus y minus f of x minus f of y less than equal to phi of xy for all xy belongs to x, and this series k from 0 to infinity 1 by 2 to the power k phi up to the power kx comma to the power kx converges, and this limit n tends to infinity 1 by 2 to the power n phi up to the power kx comma to the power ky is equal to 0. Then there exists a unique additive function capital A from x to E such that this f is near to A by this quantity 1 by 2 summation of k from 0 to infinity 1 by 2 to the power k phi up to the power kx comma to the power kx for every x belongs to small x belongs to capital X. So the following theorem by Gabruta is also a very famous researcher in the domain of functional equation, generalizes the previous theorem due to Forti and Komenick. He obtained this theorem. Let capital G and capital E be abelian group and a Banach space respectively. And here the control function phi is from G cross G to 0 to infinity. Be a function satisfying this condition, phi of x, y is equal to k from 1 to infinity 2 to the power minus k plus 1 phi of 2 to the power kx comma 2 to the power ky, which is finite for all xy belongs to G. If a function f from G to E satisfy this inequality by means of this control function, norm of f of x plus y minus fx minus f of y less than equal to phi of xy for all xy belongs to G, then there exists a unique additive function f from G to E such that this A is near to f by this control function. Norm of fx minus ax less than equal to phi of xx for all x belongs to G. Moreover, if f of tx is continuous in T for fixed small x belongs to G, then A is linear. Then Gare in 1992 studied the stability of additive Cauchy functional equation with special control function phi occurring in the inequality given above by 10. And below we give one such interesting result. Let x be a real Banach space and let y be a real nonlinear space. Suppose that phi from x to r is a non-negative subadditive function on capital X, and f from x to y is a mapping satisfying this condition, this inequality. Norm of f of x plus y minus f of x minus f of y less than equal to phi of x plus phi of y minus phi of x plus y holds true for all xy belongs to x. Moreover, if f and phi have a common continuity point, or if the function small from x to norm of fx plus phi of x is bounded above on the second category Baire set, then there exists a non-negative constant small c such that norm of fx less than equal to c norm of x plus phi of x for all x belongs to small x belongs to capital X. And this is another interesting result in the same direction due to small. Let delta be a positive number and assume that a continuous mapping f of I to us satisfies this condition. Mod of f of summation n from 1 to m xn minus summation n from 1 to m f of xn less than equal to delta summation n from 1 to m mod of xn, and here x1 x2 up to xm belongs to R. For all m belongs to the set of Nusselt number, then there exists an additive mapping capital A from R to R satisfying this condition. Mod of fx minus a is less than equal to delta into mod of x for all real numbers small x. So it is not possible to capture all of the development in this direction. So in the previous theorems, the domain of function f is a norm space or a Banach space, or more generally an abelian group. In 2005, Areola and Bayer studied the stability of the additive Cauchy functional equation in a non-Archimedean field. Then Muslian and Rasias in 2007 studied the stability of Cauchy functional equation in a complete non-Archimedean norm space. Mihet and Sadati in 2011 studied the stability of the additive Cauchy function equation in random norm spaces. Then by Hacks and Sheplinsky and Olko in 2015 studied the stability of multi-additive quadratic mapping in the setting of commutative groups. Then Bracek and E. Hedy in 2020 studied the hyperstability of Cauchy functional equation in Banach spaces. These are just a few of the contribution to Cauchy's additive functional equation. There are so many. So here now I want to show some of our work. So I have already mentioned about this work, fuzzy stability of a rational functional equation and its relevance to system design. So I have published this paper jointly with Professor B.S. Kumar, and this was published in 2019 in International Journal of General Systems. Here we have obtained the solution of the rational functional equation given by equation number 7, for which I have shown you an physical relevance. Moreover, we have obtained the various stabilities of that rational type functional equations, and moreover, we have actually demonstrated 2 physical relevance in system design. So in the same year, we have published another paper, but in this case, we have considered a mixed type functional equation. And we have also given some application for generating secret key in client server environment. So this is a function, although it looks strange, but this is a functional equation, which is a mixed type functional equation. And here we have obtained the higher Coulomb ratio stability and in fuzzy norm spaces. Moreover, we have obtained several geometrical erudition and approximation of some functional equation in numerous variables published in Proceedings of the Indian National Science Academy. Moreover, we have obtained classical stabilities of inverse fourth power functional equation. This is also a type of rational type of functional equation. Then published in this Journal of Interdisciplinary Mathematics. Also, we have published a paper on fuzzy approximation of a multiplicative inverse cubic functional equation in subcomputing. This is also a type of rational type of functional equation. So we have also published stabilities and instability of an advanced quadratic functional equation in various norm spaces published in mathematical method in the applied sciences. Fuzzy stabilities of a new hexagonal functional equation in various spaces published in recently published this one in the Journal of Ovidas University of Constantine. So here we have numerically shown the difference between various stability results. So also we have published recently approximation of Jensen type mapping via fixed point technique published in Mathematical Notes. So functional, I want to conclude my talk with some comments like this. Functional equations have appealing characteristics for designing models. Conditions required by many models in order to replicate reality adequately can be written as functional equations. Engineers find appropriate tools in functional equation for design purposes. In the process, they do not choose function arbitrarily, but functional equation appear as the only solution to the adequate set of requirements. Functional equations have also applications in various other fields. So in the reference section, I will show some such references. So there are several other stability results for various types of functional equations. So in this connection, I will show one book, a recent one. Only a few aspects of functional equations were discussed, and the names of a few contributors to the field of functional equations were highlighted in the talk. And of course, there are so many great contributions. So Jeff Azzel, so we are following his definition. This one is a very good book. And regarding the history of functional equation I mentioned about, so this all those can be obtained from this J. Azzel book. So regarding application, various applications of functional equation in applied sciences, this is a very good book for those who are interested in applications of functional equation. Published in 2005 by Elsevier, Functional Equations in Applied Sciences. So here there are so many applications of functional equation in various branches of science, engineering, and technology. And so P. Kannapan, he is an Indian origin mathematician. Application of process equation is combinatorics and genetics. He published in 2001. So this book is also a good book for various solution methods and stability analysis of various type of functional equation, published by J. M. Gracias, E. Thandapani, K. Ravi, and V.V.S. Kumar, published by World Scientific Publishers in 2017. And this one is a very good book on Introduction to Functional Equation by P. K. Sahu and P. Kannapan. Both are Indian origin mathematician, and both of them are great contributors to the theory and applications of functional equations. So this book was published by Taylor and Francis in 2011. So this is a very good book for those who are interested in functional equation. So with this, I want to conclude my talk.
Thank you for a very informative talk. I want to hand over to the audience and ask if there are any questions.
Yeah, any questions? Questions to Professor Hemendra? Yeah, just check online chart once. Professor Karin, you can say.
Sorry, could you repeat that?
Yeah, you can conclude. I think no questions, maybe.
Okay, thank you. So I'd like to thank the speaker again. It was a lovely presentation. Thank you.
Okay, thank you.
I thank you, Professor Hemendra, for a wonderful talk, and I also thank Professor Seti Howell for chairing this session. Thank you, madam. Thank you once again. So next talk is by Professor Hamid Reza, Iran. It's also an invited talk, online mode. And Professor Hemendra is chairing this session. And it is a recorded one due to some technical issues. Professor Hamid Reza has sent the recorded version of the talk. I request the delegates to keep in online mode.
9 minutes.
Thank you.
Hello, everybody. My name is Hamid Reza Moradi.
Yeah.
I'm
Hello,
a master with
hello,
expertise in matrix or
hello, Professor Hamid Reza. Hello. Hello.
Hello, Professor Hemendra.
Yeah.
Due to their country restrictions for Zoom access, they have given the recorded session. So you can just brief about the speaker, then we will play that recorded session here.
Yeah, sure. I understand now. Okay, so now I invite Professor Hamid Reza to deliver his talk. So you may now start the video presentation.
Hello, everybody. My name is Hamid Reza Moradi. I'm a math researcher with expertise in matrix or operator inequalities. These days, I'm focused on numerical range or numerical radius in Hilbert space operators. This topic is very attractive amongst researchers, which can be seen by a simple search in Google Scholar or other sources. This talk is also based on one of my recent articles on numerical radius. Throughout, I assume the audience are familiar with basic definitions and concepts of Hilbert space operators. Throughout this talk, H denotes Hilbert space and BH denotes the C-star algebra of all bounded linear operators on a complex Hilbert space H with inner product. For operator A in BH, we define numerical radius and the usual operator norm like this. The absolute value of A is defined by this term. The most important properties of numerical radius is that it's equivalent to usual operator norm. Indeed, we have the relation number 1. Notice that the inequalities in this relation are sharp. More precisely, the first inequality becomes an equality if a squared is equal to 0. The second inequality becomes an equality if a is normal. The inequality number 2 is well known in literature as the power inequality. Throughout recent years, several refinements have been proposed for the inequalities in relation number 1. For instance, Kitane has proved the inequality number 3. To prove inequality number 3, he demonstrated inequality number 4, which is stronger than number 3. The inequality number 5 is also proved by Kitane, which is another refinement of the second inequality in number 1. Inequality number 6 refines the first inequality in number 1. The goal of this talk is to improve these inequalities. To this end, we need two lemmas. The first lemma is a refinement of the triangle inequality, and the second lemma is known as the mixed Cauchy-Schwarz inequality. Our first result is the inequality number 7. This inequality, of course, is an improvement of inequality number 4. I've put its proof with details. Example 2.2 shows that this result is non-trivial. As a direct consequence of theorem 2.1, we have corollary 2.3. Again, I've put the proof with details. In remark 2.4, I have shown that how this inequality improves the inequality number 3. Theorem 2.5 is a refinement of inequality number 5. I've included the proof with details. Remark 2.6 is a particular case of this theorem. Corollary 2.8 is another refinement of inequality number 3. You can see its proof with details. Proposition 2.11 is a refinement of triangle inequality that you can see its proof. Using this inequality, we can prove theorem 2.12. Notice that this theorem improves inequality number 6. Finally, you can see the references list. Thank you for your time and consideration. If you have any questions, please contact me via this email address. Hello everybody,
I think I can. Hello.
Hello, sir. You can wind up the session.
Okay, thank you. So let us thank Professor Hamid Reza Muradi for his pre-recorded talk on new sharp inequalities for numerical radii of Hilbert space partialities. And his work shows us so many interesting refinement of the numerical radius inequalities for Hilbert space, several Hilbert space operator. So I think, hello.
Badavi wants to ask something.
He is not available, I think. So you have to ask him through his email.
Hello,
This was
Professor
actually.
Yeah, he's raising hand. Ayman Badavi.
Hello, Professor Badavi.
Yes, unmute.
I'm Hari Krishnan here.
Hello, can you hear me?
Yes.
Yeah, I just, I don't know, I want to make a comment. In the last sentence, Hamid, I thought I'm listening to a computer program like, I'm not sure if you felt the same thing. I thought it was really interesting. I like it. So I thought I just mention it.
He has given a different way of presentation, Professor Ayman.
I cannot hear you clearly, but this is, I like it. I just thought I mention it.
Next time you can also try in the similar way.
Okay, thank you.
Thank you very much. So with this session, it comes to a conclusion for our 3 days international conference on algebra and analysis and its application. So I would like to propose a vote of thanks to all the people. So first of all, I would like to thank our first day's inaugural chief guest, Dr. Narayan Sabai sir, for inaugurating our event. And next, I need to thank our beloved director for his wholehearted support to conduct this conference in a beautiful way. And also, I would like to express a sincere thanks to our HOD of Department of Mathematics, Dr. Sudhakar sir, for the full support. And also, I would like to thank our speakers, Professor Ayman Badawi, Dr. B.R. Shankar, Dr. Anuradha Sharma, Dr. Hema Sundar, Dr. Stephen Welsman, Professor Shakir Ali, Professor Davas, Professor Kent, Professor Puniswamy, Professor Bhavanari Satnarayana, Professor Om Prakash, Professor Madeleine Al-Tahan, Professor A.R. Rajan, Professor Pilch, Professor Violette Fote, Professor E.K. Narayan, Professor Mark Farag, Professor Manjunath Prasad, Professor Sam Johnson, Professor Prasad, Professor Jagan Mohan, Professor Katie Howell, Professor Hemant Datta, and finally Professor Hamid Raza Moradi for their valuable talks in various fields of mathematics. And I also like to thank the government funding agency DST and NBHM for the partial support for conducting this conference. And also my special thanks to all the delegates who attended offline from various institutes like CUSAT, IIT BHU, Aligarh Muslim University, and other institutions in the nearby premises, and also the online participants from the various parts of India, and all the teaching faculties from our department. And also I would like to thank MAHE and MIT for providing the logistic support to conduct this conference. And also a special thanks to the HOD of the Civil Engineering Department and the coordinator of this KEF R&D Center for giving this space to conduct this conference in a smooth manner for the last 3 days. And a special thanks to the caretaker of this KEF R&D Center, Durga Prasad. He is sitting in the back side. He had helped us in all the ways, all the kind of technical support, and whatever the difficulties arise, he had given a good support. So thanks to you, Guru Prasad. And a note of thanks to the staff, security, and officials of this institution. And thanks to all for your presence and support. So we wish that we will try to organize similar kind of conferences in the near future in offline mode. This is the first time we have conducted in the online and offline mode, and we have studied various things here. What are the difficulties and what are the methods to resolve that one? And I have to thank especially two people. Without them, we cannot make this event proper. One is Vinay Masoon from he's our colleague, and Uma Shankar, he's a research scholar from Department of Data Science. But here, even though he is in that department, he is working in linear algebra under the Professor Manjunath Prasad sir, who gave the talk today morning. So without their help, and all the research scholars put their effort maximum. So without their help, we could not complete this one in a hybrid mode. So next time, as we try to organize within every 2 years, till before the corona, every 2 years we used to conduct one conference. Only the corona made us to wait till 2023. So we will try to come up with a conference in 2025. We will try our best to conduct it in offline mode. So, okay, thank you, one and all. And also one more thing. For this conference, we have a conference proceedings in Palestine Journal of Mathematics. So we will mail you about the deadline of the submission. So if we tell the deadline, you can submit on or before that date. Based on the papers receiving from the authors, we will start the review process. And also, I would like to thank Professor Ayman Badawi for agreeing to publish the special issue in Palestine Journal. So thank you, Ayman Badawi. And thank you, Punanta. One more thing, we will send a link for the feedback from the participants. Please spare your 2 or 3 minutes time and just complete it. Not immediately now, we will share it through email.